Give it another minute. I only have a couple of things to say. Looks like people are starting to show up. Last time I looked, we had about 75 registered.
There was a Sizzle users group meeting thing just before this, so some people might be coming in late.
Okay. It's good to see some old friends here. Matthew Hecht, Dr. Dewar from Florida State. Let's see. All right, let me start my spiel. Hopefully Laura will be here shortly. Oh, there she is. Okay, welcome everybody. I'm gonna only take a couple of minutes here. We have a pretty full agenda and we want to get right into it. First, I want to note that there'll be a little bit of jumping between Zoom meetings this morning. We've structured our agenda around the regular weekly CGD lab seminar, which this week will be Scott Bachman and Gustavo Marquez speaking on some of the machine learning work they're doing on Eddy parameterization. So at 11 o'clock, well, we'll try to stop at 10:55 or so, and then everyone can jump over to the CGD seminar. We'll put the Zoom link and password for that should be in the invite email you got, but we'll also put the link and the password in the chat towards the end of this session. This meeting this year is also coordinated with the land ice working group. We have a session tomorrow morning on ocean ice sheet interaction. And then also we have, we're meeting jointly with the Ocean Transport and Eddy Energetics climate process team. So we have a lot of great talks from that group. So I hope no matter which constituency you're from, you'll join the full meeting. All the talks will be 20 minutes in our ocean working group sessions, at least, with 5 minutes for questions and discussion. So we're asking everyone to really stick to 20 minutes of speaking, and the moderators will let you know if we have a couple minutes left. Unless we hear otherwise, we'll assume that you're going to share your screen and run your own slides. We do ask that everyone sends their slides, preferably before your talk, so that we can drive them from our side if there's some kind of technical hiccup. And also we will post the slides on the meeting website after the meeting so people can go back and review. Also, the meetings are being recorded and streamed on YouTube, and the links to each of the video recordings of each talk will also be linked to the meeting webpage after the meeting, so you can go back and review or catch talks that you had to miss. Finally, please be respectful and constructive in your discussion and enjoy the meeting. I think I will stop sharing and turn it over to Laura, who will say a few words about climate process team and what they're expecting to get out of the meeting this week.
Okay, great. Well, thank you very much, Frank, for the introduction. Let me share my screen, and hopefully everybody can see that and can hear me fine. So yeah, so first of all, I'd like to thank the CESM community and the Ocean Modeling Working Group really for the invitation to jointly host our meeting. I'm very excited, and we as a team, the CPT, are very excited to be part of the winter program and exchange knowledge and ideas and ways forward with the community. So I'm going to start by explaining a little bit, what is the climate process team on ocean transport and Eddy energy. And so, it's a joint project with many scientists from different institutions and modeling center, and this is us at one of our regular meetings. And so the goal of the project is really to improve mesoscale Eddy parameterizations via energetics. And we're focusing on IPCC class models, in particular models from GFDL and Core and Los Alamos. So it's a project that is generously funded under the US CLIVAR, CPT by the NSF and NOAA, and really kind of pushing forward our ideas, or the ideas of the community, of how to merge energetics and mesoscalities. So what I'm going to do here, so I think I have about 8 minutes, something like this. I'm going to outline the motivation of the CPT, our goals, and basically flagging a few of the talks that'll be coming up by our researcher, and they'll go into the greater details of what's happening. And I hope we'll exchange many ideas over the next few days. So first, let's start with the basics. So why are we focusing on energetics and mesoscale eddies? So if we take a little bit of a step back and we think about where energy is being inputted in the system, so we know that most of it is happening at large scale by winds and buoyancy. And that input of energy is basically setting a large reservoir of available potential energy. And as energy cascade, if you want, towards smaller scale, mesoscale eddies are playing a role where they kind of interfere with that process. What they do is, at the deformation scale, they're going to extract available potential energy and transfer it into kinetic energy via baroclinic instability. And so what's happening then is some of that energy that has been transferred from the available potential energy reservoir into the kinetic energy reservoir is going to be backscattered, basically fed back into the large scale flow. So what we're saying here is that energy pathways with mesoscale eddies are with a big player will actually have a big impact on setting the transport, the circulation, and the stratification in the ocean. So this is really what we're after. So if we think in terms of ocean modelings, what we're saying is that if you're missing mesoscale eddies, or if you're missing some of those energy pathways in your simulation, you will have biases in ocean transport, stratification, and so on and so forth. So let me show you some of the symptoms, if you want, of missing mesoscale eddy energy. So a suite of ocean models that run at different resolution, 1 degree, 1/4 of a degree, 1/12 of a degree, sorry, 1/10 of a degree, I believe. And if we look at surface kinetic energy in the Southern Ocean or in the mid-latitude at 1 degree, you have less kinetic energy, and that's true pretty much at all scales. And again, compared to the high resolution simulation where the flow is a lot. Now, what's more telling here is actually the weak or inexistent flux of energy between the available potential energy reservoir and the kinetic energy reservoir, and also across scale. And so this is shown here in this plot. I'm not going to discuss it too much, but this is the flux of energy as a function of wave number, or if you want, resolution. So small scales are over here, large scale over here. The flat line means no flux. And that's basically a 1 degree ocean model with traditional Eddy parameterization. That means we're not transferring available potential energy into the kinetic energy reservoir, or very little. And we basically have almost no transfer from small scale to large scale. And so, as you increase resolution, those pathways kind of emerge. And so really what we're saying is that the lack of kinetic energy at all scales, or most scales, those weak or inexistent flux between energy reservoir and scales means that we end up with biases in the horizontal and vertical transport in low resolution ocean model. And again, this is just a illustration of the transport in that set of simulation. You can see the stratification and the currents are very different. And as we said, circulation is a pretty critical component of the climate system. So if you have biases in circulation, stratification, and transport, you'll end up with biases in ocean heat uptake, carbon uptake, and their storage. Okay, so hopefully I set the motivation, right? So really getting after those energetics and pathways between reservoir and scale to really improve the fidelity of the large scale transport representation in IPCC class model. This is really the aim of our CPT. And we're doing that by unifying energetics and mesoscale closures of buoyancy and momentum. And we're really going after an implementation that will be robust for models of different resolution that will target different scales and different dynamical regimes. So something that will be flow aware. Again, eddies in the tropics the tropics are very different than mid-latitude eddies. So we really need to understand those pathways and push forward the parameterization that can be implemented in different models for different resolution. So how are we going to target that? It's a pretty big and challenging project. And so we have three main threads right now, and that will be kind of the main threads of the CPT. Is one, we're evaluating consistently and continuously existing parameterizations, some that have been proposed recently, and the one that will hopefully develop as part of those CPT. And we're doing that in a consistent way by starting with an idealized configuration of MOM6 called Neverworld 2, that's been developed by Princeton and GFDL and led by Nirja Bhamidipati, called Neverworld 2. Alistair Adcroft will talk about this tomorrow. And in those simulations, what we're setting is really trying to understand and evaluate mesoscale eddy parameterization and energetics. So NOAA will show on Thursday, kind of the first step towards evaluating mesoscale eddy kinetic energy versus the mean kinetic energy reservoir, and how we're going to push forward the evaluation of our parameterizations when it comes to the kinetic energy budget. Of course, we're not going to stay in the idealized world. We're going to move towards global models, and this will happen, very quickly. Gustavo later on today will already talk about a parallel project to the CPT about evaluating current mesoscale kinetic energy parameterization, but with a slightly different flavor. So I'm not going to tell you more, but there will be more to that in a couple of hours. Now, the second strength that we're pushing forward is also unifying those closures between momentum, buoyancy, and energy. And for that, we need to understand how energy is being transferred between reservoirs and between scale. And so Elizabeth will talk on Thursday about that partitioning between barotropic and baroclinic flow. So how that energy transfer actually sets the stratification and how we should represent that in our closures, again, to be flow and scale aware in our parameterization. Last but not least, we're also curating observational diagnostics for model evaluation and also for constraining parameters. So Jake will talk on Thursday as well on how to make that first step, basically how to come up with diagnostics that are scale aware using satellite measurements and being able to evaluate how much eddy kinetic energy we have in the system and how they could help us evaluate models and constrain a parameterization. All right, so let me close by saying again, this is a big challenge to actually come up with a unified parameterization of eddy energy and of eddy closures via energetics in global models. But it's an exciting challenge. And I think it's only possible because we're a team of observationalists, theoreticians, and modelers, working across institutions to try to, improve our understanding of mesoscale and energetics in general, and to really push model development that hopefully will benefit the community. So hope that you will enjoy interacting with the CPT. I'm very much looking forward to interacting with the CESM Ocean Modeling Working Group and the rest of the CESM community largely. So thank you again very much.
We have a minute if anyone has questions about sort of the project level structure of the CPT or organizational issues.
Yeah, Brent, this is Bill Arts. Can I ask a question?
Sure.
Yeah, just on the CPT, I might have missed it, but is there also an effort on understanding the various ultimate sinks of energy? I mean, eventually it has to dissipate. So I didn't catch that. Is that coming? You don't have to get into details, just where you are on that organization.
Yeah, thank you very much. Yeah, thank you very much. That's a very important point. That's true. So there will be, as part of the evaluation, how it gets dissipated, or at least how much gets dissipated based on the evaluation. So that will be part of the project as well. Absolutely, part of the mesoscale eddy kinetic energy equation. Yeah, thanks for that question.
Okay. All right, thanks. Just quickly remind people, please mute your microphones if you're not speaking. Now that we're moving into the regular talks, if you have an urgent point of clarification or question, you can go ahead and put that in the chat. At the end of the talk, please use the raise hand function, and at least on my screen, it's under the reactions menu at the bottom. And we'll call on people in turn. So Bob, take it away. First up is Bob Hallberg on evolving plans for MOM6 development.
Great, thank you very much, Frank. So today I'm going to talk a little bit about where we're going with MOM6 development. As many of you on the call know, MOM6 is very much a community model with significant input from NCAR, the CESM community, and a number of other places. I'm going to talk a little bit more about what we're doing at GFDL, mostly because we're covering a lot of the CESM activities as a part of the meeting. Okay, sorry about that. Okay, so at GFDL, there are a couple of things that are going on. Some are GFDL specific. For instance, a lot of our focus is on key applications for NOAA. MOM6 has been discovered for operational use, and so there are a variety of different applications that are being actively used within NOAA. On the global side, we have a hierarchy of different resolutions ranging from the quarter degree CM4 up to higher resolutions that are going to be used at NOAA for weather and out to climate timescales. And so as we identify areas of opportunity for improvement with those, that's going to be one of the big foci at GFDL. But another one that's really emerging is the realization that MOM6 is actually a very useful model, especially for biogeochemical cycles in coastal areas. And there's a very large new climate fisheries initiative funded by the National Marine the National Marine Fisheries Service, jointly with OAR, that is ramping up. And so we're looking at a fairly significant activity to utilize some of the nice features of MOM6 when it comes to tracer heavy models. And I'll speak briefly about both of those. At the same time, going forwards, algorithmic development in support of these key applications and also for simple scientific curiosity is something important going forward. We have a number of activities that are going to be going on over the coming months and years, in particular the Eddy CPT that Laura just talked about. We have new activities looking at the effects of waves in driving surface mixing, internal wave propagation and mixing, and so on. And we're also looking at better approaches to coupling the cryosphere and the ocean, for instance, embedding the sea ice dynamics into the ocean and see whether that allows us to more faithfully simulate the interactions between the two. I'm not going to talk much more about these today because these are going to be covered in other parts of this session, or we could come back to this later. But in addition, one of the big activities that's been going on is really thinking carefully about how we're managing the code for the growing community. MOM6 is a community model. We want to encourage people to contribute to it. At the same time, we want to make sure that those contributions are coming in a context that's not disruptive of the other activities, and we're maximizing what we've learned in a way that actually helps people to do their job better. There are a few things that are really important going forward here. The documentation of MOM6 has improved significantly this year. There's still room to go, but I want to call out Kate Hedstrom. Thank you very much for doing a great job in kind of fleshing out some documentation of a lot of the MOM6 algorithms, a lot of the interfaces. We've gone from something that was a few tens of pages to different granularities of documentation ranging up to something that's into the hundreds of pages documenting all of the different interfaces. In addition, we've realized that with the growing community and with the growing input, that testing is something that has to continue to get better to keep up with this. And we're also really trying to highlight self-enforcing code conventions. So we don't want there to be policemen. In other words, we want people to have tests that anybody can run, anybody can evaluate. And if your tests aren't passing the agreed upon standards of what things are supposed to look like, provide feedback that help people to fix it, so that this is kind of a self-regulating community, but one where these kind of standards are really useful for helping people to really understand what the code is doing and understand things as it is rapidly growing, which it is. And then finally, I'm going to talk a little bit about some efforts that we're taking to improve the overall performance of the model as it has grown. This has become an emerging and ongoing challenge, but one that I think is manageable. So for those of you who are somewhat new to MOM6, one of the keys to its success is this vertical Lagrangian remap method, where we break up the equations into two parts, a slower part and a faster part. The blue part is the faster part. That's a Lagrangian update where the coordinates move with the flow. The second is a vertical remapping to any arbitrary coordinate you can dream up. It could be Z, it could be density, it can be anything. The only limit is creativity. And this has a number of key advantages. First off, we can basically do any coordinate you want. We can do wetting and drying. We can do, there are really no limits. Second big advantage is there is no vertical CFL limit on the time steps, which means you can refine the resolution in the vertical and still take long enough time steps to be practical for climate or realistic applications. And then the third one, which is actually really important for the fisheries side and biogeochemistry, is that the tracer advection is not required to represent the internal gravity waves. So the internal gravity waves limit the time steps for the blue parts of the equations, but we can break out the tracers, subcycle them, and take a much longer time step for the tracers than we do for the other pieces. And that's illustrated here. So there are 4 different time stepping cycles within MOM6, all of which are step forward in a Runge-Kutta-like family of time stepping schemes. But the fastest are the barotropic time steps. Those are limited by the external gravity waves. And then the second is the Lagrangian dynamics, essentially 3-dimensional stacked shallow water equations. Those are limited by inertial oscillations and internal gravity waves. And then finally, we're able to cycle that out for longer timescales for tracer advection and remapping. And what this means is that the cost per added tracer with MOM6 is vastly lower than with a number of other predecessor models. Within NOAA, there are a number of different active uses of MOM6 for operational purposes, ranging from the CM4 quarter degree 75-layer climate model for timescales from centuries to millennia, and an Earth system model where we've reduced the spatial resolution in order to give us the same kind of throughput, but with lots of biogeochemical tracers. In addition, there are variants of MOM6 being used for subseasonal to seasonal forecasting, and this is occurring both at NOAA EMC and via the North American Multi-Model Ensemble. The quarter degree resolution here is identical, although with a different coupler, to the CM4 ocean. And so there are synergies there between them. And then we have a low resolution atmosphere that's being used as part of the SPEAR configuration. And that's being done, it's heavy on the data assimilation side, and the lower ocean resolution gives less variability, which I'm told is helpful for some data assimilation. You don't need such large ensembles. At the same time, there's a 1/12 of a degree global near-term forecasting model that is being used at EMC. And there are a number of regional models that are now being used for all of the US coasts based on MOM6. So the hierarchy that we're looking at GFDL is building on the success of CM4. We're pretty happy with it. We're hoping to achieve kind of similar or improved representation of climate, but expanding the range of areas that have significant eddy variability explicitly represented by the models. And we will also have some variants which have thermodynamic or dynamically interactive ice shelves as a part of these higher resolution variants of CM4. And the basic idea is that as we go to higher resolution, the areas where the eddies are explicitly resolved is expanding outwards and expanding up onto the coasts. And so hopefully we'll be able to sustain this hierarchy. And so for a particular scientific question, you can select the configuration that is the right speed and cost for what you're trying to do. We're pretty happy with the initial results. from this 1/8 of a degree version of OM4. What I'm showing here is the 50-year change in temperature with a JRA dodo forcing. So this is reanalysis forcing from the 1950s up to near present. This is run through the 3rd cycle. And the trends that we're seeing here in the 1/8 of a degree and the 1/4 degree are both fairly similar and are broadly reproducing the observed long-term trends. So we think that the portents here are pretty good, favorable. At the same time, there's an active effort to compare the 12th of a degree MOM6 configuration with a very nearly a similar 12th of a degree HICOM configuration. Both were set up to be as similar as possible. Eric Chassignet is going to be speaking momentarily in much more detail about this. But I think the key point here is that the comparison between these two, they're very similar in their overall structure, but there are differences in details of the implementations. And this is strongly suggesting areas where we can learn from the comparison to improve MOM6. Well, at the same time, these are broadly both capturing the large-scale dynamics of the ocean. And so this is, I think, promising as an avenue for possibly combining efforts and unifying large-scale global ocean modeling capabilities across the United States government, while paying particular attention to each agency having the ability to adapt what it's doing to meet its own particular mission needs. Some of the parts of the comparison that are particularly interesting, there are differences, for instance, in the overturning, Atlantic meridional overturning circulation between these models. There are differences in the Gulf Stream, there are differences in things like the shedding of loop currents in the Gulf of Mexico. And these are suggesting specific changes to try out in MOM6 to make it work a little bit closer to HICOM and see if we can use that as a way of guiding our development. And in particular, in the case of the overturning, we're looking at things like how you represent lateral drag near topography, how you define the vertical coordinate and how aggressively you remap to that arbitrary vertical coordinate, and some of the details of the bottom boundary layers. And with these set of changes, for instance, we are seeing clear differences in this figure from H.L. Kim of the near bottom temperatures after 10 years of simulation from differences between these models. So that this is, I think, a really beautiful illustration of the power of the community coming together, being able to do detailed, close comparisons. In this case, it's between two different models, but we'll be doing the same thing, for instance, between, say, NCAR's and GFDL's coupled climate models, where we're deliberately choosing to try different avenues for parameterization of different processes, and then we can compare and figure out what's going to work best and learn from it collectively. At the same time, there's been a really significant push over the last couple of years and a very large community, dozens of people coming together to explore the use of MOM6 and its advantages for tracer-heavy models, for regional models, in particular looking at questions about how fisheries are going to be impacted by climate. And we have a number of configurations here. Kate Hedstrom, I believe, is going to be talking about this Arctic configuration a bit later on, but there are also regional configurations covering kind of this northeastern part of the Pacific, a west coast of the US, northwest Atlantic. And these are fairly close to some configurations that have been run for quite a while using ROMs. But the big advantage to MOM6 is the fact that the tracers don't have to take the same short time step as the dynamics, means that in a tracer-heavy model, like a fisheries model, the cost is dramatically lower than with its predecessor. And so this is really something that opens up the possibility to expand the use of the model because it's cheaper, to do more ensemble members, carry out more experiments, or increase the complexity of the biogeochemical cycles. And so this is something that's we're pretty pleased with. Now, this has involved having to take on the treatment of the open boundary conditions. In a Z-like model, the open boundary conditions, or a terrain following model, the open boundary conditions seem to be working quite well. This is the entire Northwest Atlantic regional regime, and the open boundary conditions here are evidently behaving as intended. There's some questions about how you treat open boundary conditions when you use more exotic vertical coordinates that may be moving with time and have definitions that vary in space. And so there's still some active work to be done, but again, this is something that's promising, and a number of people have come together, and we're making a great deal of progress in understanding what's going on. And I want to credit Ralph Dewson for this animation. So the idea here is that there are a wide range of different fishery-related decisions that occur over a range of spatial scales and different time horizons, and many of them are already being covered, for instance, by the National Ocean Service at the shorter time scales that have active operational models. At the same time, these larger scale, longer time scale questions are something that is coming from this new capability. And the idea here is that this Climate Fisheries Initiative is going to be facilitating a cross comparison across these range of scales, detailed comparison. We are going out of our way to make sure that we don't disrupt any active operational uses, while at the same time exploring the possibilities of whether we can gracefully transition within NOAA to using very similar tools and mutually supportive tools across a wide range of different scales. And so this is something that's going to be moving forward, but again, being very careful not to disrupt anything that's actively going on and is in active operational use. So I want to just take the last couple of minutes here to say a little bit about some of the things we're doing on the software side to help facilitate and manage this growing group of people that are contributing. So we are convinced that open development is working, that this rolling deployment of things that are actively going on, along with careful testing to make sure that nobody's configurations get broken, that we make sure that we're not stepping on each other's toes. This is working, and it's growing. We're up to 128 different forks off of MOM6 as of yesterday. Within that, there are at least 5 major hubs and partners that are actively evaluating to make sure that the things that they're caring about don't never get compromised by any changes coming in. And what's really exciting to me is that the number of people who are actively contributing is growing and growing dramatically. We're now up to 25 people who have contributed more than 1,000 lines of code. Some of these are changes to the code. Some of them are whole new parameterizations, and you'll hear more about those over the next couple of days. But the critical thing here is this is all done with a very flat, very small d democratic structure where all the synchronization is happening by consensus. And as part of that consensus, we have a combination of regression testing specific to each of the hubs and their computers to make sure that no important applications are ever disrupted. But at the same time, there's a growing set of self-consistency testing that we can carry on either as an individual or that get triggered whenever anybody says, I have something I'd like to contribute. And the beautiful thing about this self-consistency testing is it is objectively either passing or failing. It can happen on any computer by any person. It can be triggered by anyone. And so any user who has something that they want to contribute can run it through this self-consistency testing. And there's a whole set of these, but basically it makes sure that it reproduces across orientation, across restarts, taking your index space and rotating it, you get the same answers. How you're handling
about 2 minutes, Bob.
Okay, perfect. How you're handling the memory, and if you fail, it's something that's wrong, you get the feedback, you can correct it yourself. Now, the nice thing about this is that this robust testing is also something that's going to facilitate porting between computers, between compilers, and also between underlying infrastructure packages. So as we move forward, we've increasingly encapsulated the FMS infrastructure calls in one place. That will enable us, if somebody wanted to put in the effort, for instance, to try replacing the FMS infrastructure with ESMF, if that's something somebody wanted to do. FMS is being replaced within GFDL by FMS2, which changes how I/O is being handled. but we're going to be supporting both of these for the foreseeable future so as not to disrupt what people are actively doing. MOM6 is already working with 4 different interfaces to different couplers, and this new code structure is going to facilitate the use of different infrastructures. At the same time, we've been doing a lot of work to go back and look at the performance of the model. One of the things we've noted is that for the same configuration, some of them have slowed down a little bit, some detectably, but at no point is it obvious exactly what jump it is. And so Marshall Ward in particular has been doing a lot of profiling of MOM6 to look at where it's spending its time and looking for localized hotspots. And some of those have evolved, and that's been instructive in terms of some of the code structures that we're using and suggest improved performance. So this is one example, and I know it's a little hard to see with the black background, but where as we added lots of new options for dealing with the horizontal viscosity, that emerged as an area that was a hotspot, even though it was doing exactly the same calculations. And it turns out that as we've added more and more options on the inside of some of our do loops, it appears to be getting past some bounds that maybe the optimizing compilers can see. And so Marshall was able to identify this as a hotspot and suggest an alternate structure where instead of putting the do loops on the inside and having the shared loops, you put them on the outside. And so Marshall's advice is say no to do if end do, and instead say yes to if do end if. In other words, move the logic out, help the compilers. And this is something where a structure that may have worked when we had 1 or 2 or 3 options, as we go to more options, becomes significantly more costly. At the same time, we're actively looking at tools, in particular this tool called Flint, to go through to analyze the code and look at code style and structures. We're particularly concerned with making sure that people are putting in parentheses if you're doing multiple adds. That helps you to give, the added parentheses helps you to give reproducibility across compilers, across computers, across deployments, say, to moving from the current message passing to different newer exotic types of computers, and to enforce the documentation. Right now we require that all arguments be documented. We'd like to move towards requiring that all real variables be described so that the next person who comes along who can read the code can helps them to make sense of what's going on. So the broad message here is that we have a very large, diverse, and growing group of people contributing to MOM6 about which we are delighted. We are working to make this as graceful and smooth as possible, to encourage people to contribute, and at the same time, make sure that as we get people contributing, we have the sort of rules of the road that help make sure that everything continues to move smoothly. So we think the open development is working, but perhaps one of the key points of discussion that I would welcome is what can we do to make it work better? Thank you.
Great, Bob. Questions for Bob? We have a couple minutes.
You want me to stop sharing, Frank?
You can leave it up for the moment.
Okay.
Any questions for Bob?
So Bob, yes, I have a question. I would like to point out that this talk was not that long ago a pipe dream, and it's fantastic to see it realized. So thank you very much, and to everybody involved. But you did mention in passing coastal.
Yep.
And the real coastal people are doing adaptive grids. And it is a whole work, and just where is the plan on that? Because that might really change your paradigm a little. So what's your thought?
There's regional and there's coastal. So, and here I'm looking at what is done operationally now by the National Ocean Service. So there are these large regional configurations, and I'll go back. The map is, I think, useful. These large regional configurations are using structured grids, and that's being done now. It's using ROMs. Those structured grids are used to drive, say, FECOM or ADCIRC for different applications when you get right up into the coastal areas. And so for now, at least, the idea is that MOM6 and the fisheries, the tracer heavy models, would be taking on these regional configurations And these regional configurations would be driving the really inshore coastal models with the adaptive grids where you can really target your resolution right up into every estuary and around every pier and everything you care about. And so for now, at least, there's still these two different structures that are working together now, and we think for at least a while they'll continue to work together in the same way. But
well, that makes a lot of sense, actually. So I'm glad to hear that. So.
Yeah. But that's an excellent question, Bill.
Okay, I think we need to move on. Next up is Eric Chessignay from Florida State. We're seeing the speaker view, Eric.
Yes, I just realized that. Sorry. Let me do it differently. Sorry, I just rebooted the screen. Okay. So thank you, Bob, for this introduction. In a sense, you summarized some of the work that we've been doing in collaboration with Florida State, with NOAA and GFDL in particular. So what I'm going to dig in is a little bit more in the representation of the AMOC in MOM6. This is work performed by Alan Walcraft and Hazel Kim at NOAA. So the main motivation was already introduced by Bob. HICOM, was the first used ALE-based model. It's not the only one. MOM6 is very similar to HICOM, but has more modern numerics and coding style, and now a much larger developer base in HICOM. So, but MOM6 until now has primarily been used for climate application. At least was the built for climate application, when HICOM has been mostly used with eddy resolving configuration for ocean prediction. So the goal was to look at the twin MOM6 and HICOM eddy resolving global ocean simulation and see how they compared to each other and what we could learn from the comparison. So we used our classic 1/12 degree configuration, which is used by the Navy Global Ocean Forecasting Systems with 41 hybrid layers. A transition from isopycnal to Z. I mean, HICOM has an option for sigma coordinates as well. We start from the same climatology. We use KPP, and we use a CFSR. 2003 repeat forcing. Every year we repeat 2003, and using the large and Jaeger. The main difference is that HICOM is fully non-Boussinesque when MOM6 is Boussinesque. There is a non-Boussinesque option in MOM6, but I don't think it's fully operational yet. The equation of state is different, as well as we use potential density with thermal velocity correction versus in situ density in MOM6. The isopycnal targets differ. In HICOM, you keep layer averages when you focus on layer interfaces in MOM6. No slip versus free slip, and in this particular comparison, we use the size 4 and CIS2 in MOM6. The model parameters were tuned what we're currently using in HICOM and may not be optimal for MOM6, and more on that later. So like Bob showed, the snapshot, when you look at the surface circulation, I mean, they look reasonably, very close to each other. There's not, some subtle differences here and there. Overall, HICOM is slightly faster than MOM6 per time step, but MOM6 is stable with a significantly longer bark length time step. So the end result is that MOM6 is about 1.5 times faster than HICOM. So the main thing that we looked at is the AMOC. Traditionally, like GOLD or HICOM, isopycnically based coordinate ocean models, when you create dense water in the Northern Sea, goes through the Denmark Straits and sinks all the way to the bottom, you have to prescribe some kind of diapycnal mixing in order for the layers to mix. So usually, those class of models had a fairly deep AMOC, in some cases too deep. On the left is a HICOM that has a maximum, that has a zero threat reps at about 3,500 meters, which is a little bit, higher than what the rapid array would suggest, which is about 4,300 meters. But MOM6, for the same configuration, after 10 years, showed a fairly shallow AMOC, which is resembled, traditional AMOC in Z-coordinate models. So we wanted to know a little bit more what was happening here. But, in last, the Atcroft et al. 2019, similar shallow AMOC was found also in the quarter degree and half a degree configurations. So here what you look at is the potential density, the density at the bottom. On the right is a climatology for January, and the others are yearly averages. But you see that the density at the bottom, in the bottom layer, is quite much more denser and a little bit closer to the climatology than in MOM6. Now we're going to look at a section here, where you have the black line, and climatology for January. So please ignore the surface field since the others are yearly average. But you see that the dense cold water that is in climatology is still present in HICOM, but it's gone in MOM6. And similar, going from the fresh to saltier transition in the vertical that is present in the observation is completely gone in MOM6. So possible causes, like I mentioned historically, when you're using isopycnal, should have a deep overturning circulation. So the main differences are size versus SIS2. The vertical viscosity was both based on KPP. We played a little bit with those to make sure they were identical. That didn't make much of a difference. The vertical regridding takes place a little bit in HICOM. You keep the density in layers at target sigma 2 potential densities, when MOM6 focuses on layer interfaces. And the other thing is that in HICOM, we had a relaxation to the displacement. So when you regrid in the vertical, you just don't move the isopycnal the full distance, but you do it by increment. MOM6 does not have the same option, but have something that is a regrid time scale that is closest. So what we did, we went to an Atlantic MOM6 domain, and that has relaxation to climatology at 80 north in buffer zones and 28 south. And that also eliminated the need for, to identify if the proper water masses were not formed in MOM6 and further in the northern part of the domain. So on the left, you have the global MOM6, and on the right, you see the Atlantic MOM6. So it's same parameters, same everything. And you do see the overflow getting a little bit deeper at 2,900 meters, but still quite shallow. So some improvement in TNS property upstream do matter. Now, this is the same simulation on the left, the original, the set parameters, and then the on the right with the regridding option that was implemented by Alan Walcraft, and that's also I think what Bob showed for using an A-choice simulation. In this particular case, you see a significant improvement in the sense that the AMOC is now deeper at 3,400 meters, still shallow, but better. And here's again a comparison between the HICOM AMOC to the MOM6. HICOM is still significantly deeper in the interior than when compared at 26 north. So if we look at the near bottom potential density now, you see that MOM6 is able to get even denser as dense as the climatology, even denser now than HICOM. And if you look in the vertical, same thing. You know now that we're able to retain the temperature, the cold temperature at the bottom, still very, very mixed salinity in the vertical. And that's something I don't fully understand why it's the case, since you're able to do better with temperature, but not in salinity. So the next step is the work that H-Oil Kim did, which used, again, a similar MOM-SIS2 configuration, but instead of using the core normal year forcing, and here is all the regrade, all the changes that were made following Alan Wallcraft's suggestion. And that's a global simulation that Bob presented. But for some reason, when implemented in the global for that specific configuration, there were pretty much no changes in the depth of the AMOC. There were some changes in the potential density, so it is effective. But represent here is the vertical, so it's not as pronounced as what it was in the Atlantic, but you get significantly deeper, colder temperature in this configuration. So that relaxation time, grid time scale is not, does not fix everything. So in summary, we're comparing, MOM6 to that was initially developed for more, climate application to a high resolution HICOM. The main difference was a shallow returning circulation. So we don't fully understand the difference. One option, and but Alistair, they've done a lot of testing that the diapicnal mixing induced by focusing on interfaces instead of layers should not really be the case. But it's still possible that the way it is implemented now, that there's more numerically induced mixing. And the other one that I haven't talked much about is a bottom boundary layer formulation, because the other major difference that we see is in the Gulf of Mexico, the loop current eddy shedding that is not occurring that often, and also the eddies dissipate very fast, and that we identify that we were able to point toward the bottom boundary layer formulation, that it mattered a lot in that specific case. So it may also matter a lot in the overflow. So our future plan is to continue to work with GFDL and the National NOAA National Weather Service to improve the realism of the global 1/12 degree with the intent of adding data assimilation in their system. Thank you.
Thanks, Eric. We have plenty of time for questions here. Gokhan, you have your hand up.
Yeah, Eric, it's coming, you touched when you said bottom boundary layers, but have you looked at sort of the impacts and representation of the overflows? And neither simulation with 1/12 degree horizontal and vertical grid cannot resolve the physics of the overflows. So what are your thoughts on that?
So we have, for the, sorry for a second. We have not looked at the detailed how the TNS evolve in the overflow. But if you have a purely isopycnal, then when you have dense water upstream, when it flows down in the overflow, it should not mix with the interior except what is prescribed by KPP. And usually it is not too strong. So that's, I think MOM6 is slightly more fancier bottom boundary layer than we do in HICOM. Alistair, Bob, do you want to?
In one of the simulations that you showed, it looked like dense water was coming from the overflow region, but it was disappearing quickly. That may indicate that there's too much entrainment or something.
Right, so that's what we don't know, what is numerically induced versus what is prescribed.
Okay.
Bob, you turned on there. You want to add something?
Yeah. So with respect to the bottom boundary layer, as Eric notes, that in pure density coordinate, the vertical resolution issue is not a problem the way it would be with a Z coordinate model, because the resolution migrates. And in comparisons, going back to an earlier CPT GoCan that you and I were both a part of, one of the things we found is that if you are representing things in a pure density coordinate, you can reproduce a lot of what you're seeing in a Z coordinate model at much higher resolutions, in part because these plumes are kind of spread out kind of laterally along the slope in density space. And so the horizontal resolution is less of an issue. It's more the vertical resolution of that interface atop the two layers that matters. But I think that the point that Eric has really highlighted here with this is the definition of exactly where you put those layers. This is not a pure isopycnal coordinate model in the traditional sense. Seems to be contributing to mixing. It's not the same as with the traditional Z coordinate problems that for instance, you fixed with this overflow scheme going back about 10 years. It's a bit different, but it does say that we probably need to go back and re-examine these same problems that we thought we had dealt with a decade ago.
Well, if I can add, I mean, in HICOM, if you have an isopycnic layer, it will remain isopycnal unless KPP mixes it. In MOM6, because you're looking at interfaces, you do not guarantee 100% that you're going to keep the layer isopycnal. And correct, Bob?
That's right. Although you can run MOM6 in the HICOM-like mode, where it's a sigma 2 layer-centered model as well. So we could do those idealized studies. But I think, Eric, you're very much onto something, highlighting this different definition of the coordinate. And so I think this is something where some brainstorming about ways to use something that's kind of focused on the interfaces, but also respecting this very adiabatic limit is something where a little creativity could go a long way.
Yeah, I think that's a point. I mean, how adiabatic is MOM6 in this configuration versus the others?
Thank you.
Questions for Eric? I had a question, Eric. You focused on AMOC. Is the problem generic? Do you see it in other flows, overflow areas? Is the neutral density surface for med outflow also distorted, or is, or Southern Ocean bottom waters?
That's a good question. No, we have not looked at those regions, so we should do that. The other main difference is in the Gulf of Mexico, and that's definitely linked to, we use a very simple quadratic bottom drag, and there is, in MOM6, there is a similar formulation, but there is evidence that they do not behave the same, the two models. Therefore, the low current eddy shedding is pretty much shut down in MOM6. So, no, we should look at the other regions as well.
Thanks. Any more questions for Eric?
Yeah, Eric, could I ask a bookkeeping question? In this overflow work that's been done in these kind of ocean models, there is this salinity restoring at the surface issue. Those used to be tuned to the nth degree to make things look as good as possible and different from model to model. What are you doing in these comparisons? Are you doing the same thing, none? What are you doing?
Same restoring. I forgot what the time scale is. It's
in both models.
In both models, it's identical. I think it could be maybe a 30 days or a 60-day restoring.
Okay.
Okay. Any last questions? We're a little bit ahead of schedule, which is okay. Okay. Thanks, Eric. I think we'll go ahead and move on to Kate. And that'll give us maybe a few more extra minutes for people to jump over to the other 11. So Kate, why don't you go ahead?
Okay. Let's see. That one.
Perfect.
That up. Okay. Hi, I'm going to talk about a pan-Arctic domain. And this domain is a grid that we set up using the ROMS model some years back. And so the idea was to run the same grid with MOM6 and see how it compares. And so a year ago, it was blowing up and I didn't know why. And there's been help from Bob Hallberg to get it so it can now run stably for a year or more. And since in the past year, Andrew Ross contributed the title code, so I'm using that. And I switched from 50 vertical levels to 75 to get better surface resolution. And I also copied over the retuning of the surface boundary layer code. It's not KPP, it's the EPBL. And my MOM6 files are available at GitHub. And so for this domain using MOM6, my initial conditions and boundary files were produced by Liz Drenkard using the Python scripts that Raf and others have been working on. And there's still a few things to do to clean up before I can take on a 40-year long run, which is one of the goals of this project. The grid is shown here. Well, this is the domain. It's, you see my cursor? So the Bering Sea is at about 5 kilometers resolution, and the resolution gets coarser as you go to the other side, to the Atlantic side, to over 9 kilometers resolution. And this, we may build a new grid for the Arctic if we need better resolution and more coverage on the Atlantic side. And this is showing the surface elevation, showing that the tides are looking tidal. And we do get tides in Cook Inlet since Andrew gave me his better scripts because his prior script had a bug in it for producing the boundary files, the tidal boundary files. There's in the middle of the Atlantic or the Arctic, there was an AJAX project back in 1975 where they had an ice camp looking at ice dynamics in the midwinter. And so a midwinter temperature salinity profile for this central Arctic is isothermal down to 50 meters with near freezing temperatures. And then also well mixed in salinity and density. And then in the summer, there's some very slight warming back at that time and slight freshening as the ice melted. And then again, goes back to the well mixed freezing temperatures in the winter. And this below 50 meters, there's a slight warming due to Pacific water. And then it's again cold down to about 200 meters depth. And then below that, you get the warm Atlantic water. And so what I get at that point in MOM6 for a year is shown here. So time is the horizontal axis and depth is the vertical axis. And I do get these near freezing temperatures until it's slight warming in the summer and then it gets cold again in the fall. I don't have quite the same structure because I don't have the a warm Pacific blob and then a deeper, colder blob. Instead, it's just slowly getting warm with depth. But that's, I believe, comes from my initial conditions, which were generated from soda. And then here's the salinity structure where you can see the slight freshening in the summer. And then going back to the slightly saltier in the winter as the ice forms and the brine gets rejected. But I do maintain a strong halocline, strong enough to keep this warm water below here 200 meters from melting the ice. This is when I had 50 vertical levels. And so you can see the 10-meter resolution at the surface. And going to 75 vertical levels, but using much of that improved resolution near the surface. So now I have 2-meter resolution right at the surface. And it's pretty good resolution down to about 50 meters. And my cold water is slightly deeper, and that's in part because of the better resolution, but I also changed the tuning of the EPBL parameters. This is the surface relative vorticity, and showing, get the strong boundary currents one would expect. And also there's some issues along the boundary on the Pacific side, less so on the Atlantic side. And so there could be improvements to the boundaries, but overall we're doing as well as we did with the ROMS model in terms of the boundary behavior. So that's pretty satisfactory. Oh, whoops. This plot from Seth Danielson is based on observations, and there's strong boundary currents. And so in the Chukchi, you get flow along these channels, the central channel and the Herald channel, and then cyclonic or clockwise flow around Hannah Shoal. And then here's the Beaufort Sea, where here's the shelf break out here. And so Seth is working on looking at the fluxes through Bering Strait using observations in the ROMS model. And so we'll be comparing that to MOM6 as well. And here's again, the surface relative vorticity. So again, I'm getting these strong currents along the boundary, but there's a lot of response to synoptic storms and just very fine scale features out here in the deep basin. Oops. This is a north-south transect through Wrangel Island, which was this island here. Salinity and temperature. And just an annual cycle. You can see there's this cold water in the deep basin at the surface and some warming on the shelf during the summer, and then it gets cold again in the fall. Oh, I see. Okay. Oh, this is the higher resolution. And again, I get deeper mixed layers with the higher resolution and the retuned EPBL parameters. This is ice concentration for a year. So you get pretty reasonable ice extent, considering this was back in 1980. And you freeze in the fall. But to my eye, it seems like it's just solid white in the interior of the Arctic for much of the year. And that's different from what I'm used to seeing in both satellite images and in the my prior ice model, where it would open up leads along, especially coastal polynyas. And this is a satellite image. Here's Point Barrow and Icy Cape. And this is Hannah Shoal with the clockwise circulation around that. And then there's strong flow along Barrow Canyon and out into along the coast, and then some splits and goes along the shelf break to the north. And so the ice model we have doesn't produce such fine scale features. Maybe we need better resolution for that. Okay. This is what the reality looks like. Computers and codes. I've been running this on Chinook, the local supercomputer system, the Linux cluster. And I tried and failed to get CESM to run on our local system. It does run on Cheyenne with the MOM6 SICE and using the new OPSI coupler. And so my current plan is to port the Lemieux landfast ice parameterization into SIS2. And this would allow me to continue using MOM6 with SIS2 on our local system. I have one of my projects for which this Arctic is, why I'm running the Arctic is looking at landfast ice parameterizations. So I need to have at least the Lemieux landfast in there. And then the plan is to evaluate that, compare that to the data, and then see if we can create a better landfast ice parameterization. And that could be either in SIS2 or SICE, depending on what I'm running. Doesn't really matter. It's other plans to improve this simulation are to turn on the sponges from NCAR to see if that helps clean up that Pacific boundary. And I have a shortwave, long wave issue at 190 degrees longitude. And that's just some feature of FMS where it doesn't believe that your atmospheric fields could be reentrant if your ocean model is not reentrant east to west. So SIS2 doesn't have leads until late spring. And Matt Harrison is looking into seeing if he can fix that problem. And other plans include comparisons to data. And Seth Danielson has been collecting Arctic data and for many, many years. And he's got a paper in Frontiers in Marine Science with comparisons to ROMs and in the Arctic and data. And I'd be happy to answer any questions and talk to anyone who wants to talk about how to set up a regional domain that's not part of the supported domains in CESM. So there's some work to do when you bring in a new domain. And of course, Gustavo can help with that too, and Alper. So that's where I'm at.
It's Kate. Questions for Kate?
This is Tony Rosati. Kate, did you look? You didn't mention anything about sea ice thickness.
No, I didn't mention that. It seems reasonable. I mean, I haven't done any real comparisons to data. There's not a whole lot of data, but it seems reasonable based on what I know about Arctic thickness, or sea ice thickness.
Yeah, I'm just thinking about prediction, and that's a big problem, is getting the thickness right.
Yeah, well, we plan to do a 40-year simulation, and then we'll be looking at how the thickness evolves over those 40 years, because of course we lost a lot of sea ice in that time.
Thank you.
Any other questions? So Kate, it looked like your cases were they Z star or sigma? What was your target grid?
It's Z star. Alistair's advice was to go for Z star because they've been having problems with the HICOM like vertical coordinate in the Arctic. Just getting the right target levels.
Okay,
I had a question, Frank.
go ahead.
I guess, why did you go after increasing the vertical resolution in the ocean model as I gather, it might be one of your first steps, because there might be so many other things that you could have played with, such as restoring of salinity or sea ice parameters. And I was going to ask the same question that Tony asked. I would be curious to see the sea ice thickness distributions.
Well, it just seemed to me that 10 meters resolution wasn't doing a very good job because, well, what I'm used to looking at is my ROMS model where I had all those sigma levels on the shelf. And a lot of our data is on the Chukchi shelf and in the Beaufort shelf. So it just seemed, talking to Seth Danielson about that I would need pretty good surface vertical resolution in the ocean to reproduce what is happening in the real world with such thin, fresh layers that come across from the rivers. I guess it's a bias about what we're used to looking at.
What is the restoring time scale or length scale and length scale?
Restoring for which?
For surface salinity.
I have no idea. I don't know if I'm using any.
Okay, Dave, Bailey?
Yeah, sure. Kate, you and I should probably have a conversation about this offline at some point, but I'm wondering about this configuration of SIS2, and I mean, have you moved to this fully embedded ice that Bob has talked about a lot? Is maybe Bob can answer that better, but I just wanted to know what you were running in this configuration.
Well, Bob has talked about that, but it's still future plans. There's no embedded ice at this time.
Okay.
Do you want to expand on that, Bob?
Yeah. So we have a couple of intermediate steps where we're doing more rapid coupling of the dynamics back and forth between the ice and the ocean than the thermodynamics, and also kind of changing around the order in which they cycle. I don't know which specific settings Kate is using for her runs, but that's kind of a halfway point towards actually moving the sea ice dynamics into the barotropic solver of the ocean. And those are things that we believe will improve the stability of the ice-ocean coupling, but you still have the issue that there's a gravity wave speed that has to be compared with the coupled time step, whereas the full embedding is something where the gravity wave time step is the barotropic time step, and it seems to eliminate a lot of the instabilities. But it does appear to be somewhat more stable. It just doesn't completely fix the instabilities once the ice is exerting a full weight of pressure. Kate, in your case, is the sea ice actually displacing water for the purposes of gravity waves, or is it effectively kind of levitating as is traditionally done?
Which would that be? I don't
there's a maximum pressure that the ocean is allowed to feel from the ice. And so, for instance, in CM4, we set that to 0 so that the ice effectively doesn't participate in the ocean's gravity waves. It's another way to eliminate ice-ocean gravity wave coupled instabilities. but one of the things it would mean when we're thinking about, for instance, the land fast ice, is that the ocean can't essentially squeeze out all of the water beneath it to touch the bottom.
Yeah, I'd have to check. I don't know.
Okay.
I mean, I've inherited a lot of parameters from other domains that I didn't set up. So
The other topic too that would be good to talk about too is the coupling, because we're now finally getting to the point where we're thinking about doing actual salt coupling between the sea ice and the ocean, and people haven't really done this before, and so we want to make sure we're doing this in a conserved way with the natural boundary conditions in MOM and so forth.
how's it going with the size 6?
No, I mean, actually, I've got size 6 running very well in CSM2. I don't have it coupled to MOM at this point, so I'm still running with size 6 and POP. But at this point, I want to make sure that size 6 and size 5 generate the same sea ice climate, and then at which point we can move forward with size 6. So.
Okay, any other questions for Kate? We have about 15 minutes before the seminar, so there's time for other discussion. Bob brought up the point of, getting feedback and looking for ideas of building the MOM6 community. This morning's session, we did, cluster talks from the broader MOM6 community, not just CESM, and we would like to continue to do that as we can in the CESM meetings to, get participation from the broader MOM6 user base. In addition, I just put a link. We're hosting a MOM6 forum on the CESM forum website, and again, we welcome questions and discussion from the broader MOM6 community there. We've talked about this in the MOM6 developer calls, and we're going to try and focus groups' questions and discussions into that forum so that they'll be recorded for people to reference in the future. So please feel free to participate there. Anything else before we jump over to the seminar? Okay. So the seminar starts at 11. That runs till noon. And then we will reconvene on this Zoom link at 1 o'clock with sort of a cross section of talks on ocean climate analyses and research. So I will see everybody on the other side.
Hey Ryan, that looks good. It's just got your picture on there. I don't know whether you care or not. And a weird white bar on the left-hand side.
What is it better now, or
Yeah, it's still got your picture.
should it have my picture in it, or?
It does, yep.
Let's see. All right, how's that? Is that better now, or still the same?
It's still the same.
So where's it showing my picture at?
On the right-hand side.
Oh, yeah, that's normal, just because I'm sharing the screen.
Okay.
Yeah, but
Oh,
the white bars and stuff weren't supposed to be there, but I think I got it fixed.
Oh, I changed my view. Yeah, now I just see the slide. So perfect. Thank you.
Mm-hmm. And there was a question in the chat, but I can't pull it up now for some reason.
I answered him with the.
Oh, okay, cool.
But then I was realizing, does the chat show up on the stream?
On the YouTube stuff?
Yeah.
No, and then I can't see it because I just joined it either. I just see that most recent.
Okay. I had a bit of a stressful moment thinking I was putting out Zoom links and shouldn't. So as long as
that person looked like they left anyway, so. Huh.
Yeah. Oh, good. Maybe they went to join the seminar.
All right. Well, yeah. So everything's looking good now. So I think we're good to go.
Yeah. Great. And I'll just message you if anything comes up weird in the afternoon, but we'll just keep, oh, I guess I'll need, if right before 1, if you can pop on and stop sharing.
Mm-hmm. Well, the other thing is like, if I'm not here, if I'm not around, you can make me stop. You can force me to stop sharing anyway.
Oh, that's true. I'm the
You hit
host.
the more next to my
Yeah.
name, you should see a stop sharing button.
No, when I click more, it just says stop live stream. But let me see if you,
No, in the participants list.
okay.
If you
Oh,
hover over
that
my
more,
name and hit the
okay.
more.
Yep, I can do that. Okay.
Okay. Yeah, I mean,
Perfect.
I'll probably be around here, but just in case, it was good to know that because people ask me that, and I'm like, well, you could just, if you share your screen, you'll stop me.
Yeah, no, that was a good reminder. Too many details in my head right now. Thank you. So yeah, so I'll just message you if something weird is going on, but otherwise we're good. And I'll be here instead of in the admin meeting. But Laura knows that.
Oh, is that today?
Yeah,
Oh, okay, cool. Yeah.
the
All
first
right.
of
Well,
the
yeah.
month
I
is,
mean, I'll be hanging around, but if you say something in here and I don't respond, just shoot me a quick chat and I'll hop over.
okay, sounds good. Thank you.
Yep. Yeah.
Are we delaying our start a few minutes because of the seminar?
Hi, we are currently on a lunch break and we'll return at 1 p.m. Mountain Time.
Okay, thank you.
You're welcome.
What time is it now, Mountain Time? Sorry, what time is it now, Mountain Time?
12:13.
12:13. So, okay, thank you.
You're welcome.
Time for tea on the East Coast, Steve.
Yeah. Good to hear you here, Mike Bell. Well, he was.
You're welcome to chat, but just so you know, it's still streaming on YouTube right now. We don't want to turn it off because it might not stream this afternoon sessions.
Okay, we're still a little bit light on attendance. I'll give it another minute. Steve, are you ready?
Yes.
We can get Ryan to stop sharing. Let's go ahead and get your title slide up, Steve. We'll give it just a minute. Elizabeth, I don't seem to be a co-host anymore. If you could, I don't know that I need to be, but just in case. Okay, well, let's get going here. I think people are rolling in. Welcome back. And this afternoon we have, oops, I already lost my page. 1, 2, 3, 4, 5 talks on a variety of ocean climate science. And we'll start off with Steve Yeager talking about low frequency variability of AMOC. So go ahead, Steve.
Yeah, I'd like to present some results coming out of the IHIS project. And I'd like to acknowledge all of my co-authors on this work. So just by way of setting the context, we're probably all aware that recent OSNAP measurements show that the eastern subpolar gyre dominates the mean and monthly to interannual variability of AMOC, not the Labrador Sea. And this was the result of this science paper led by Susan Lozier, in which she reported on the first 21 months of OSNAP measurements taken across these two array lines, OSNAP West and OSNAP East, shown in red here. And what the measurements show is that the overturning in density space across OSNAP East is much stronger and dominates the variability compared to that across OSNAP West. And so this paper was touted as a sea change in our view of the overturning, insofar as it drew attention to the transformation that takes place in the eastern subpolar gyre as opposed to the Labrador Sea. And since then, other recent observational work has underscored the importance of water mass transformation in the Erminger Sea in the high latitude closure of AMOC. I've listed a couple recent papers here, one by Chafik and Roski, in which they state that the production of dense overflow water in the Nordic seas is key to the state of the MOC, not the Labrador Sea. And then another one by Tillis Petit and Susan and colleagues, reiterating that the prevailing hypothesis is that dense waters formed in the Labrador and Nordic seas are the sources for the AMOC lower limb. However, recent observations reveal that convection in the Labrador Sea contributes minimally to the total overturning of the subpolar gyre. Meanwhile, climate model studies have long emphasized and continue to underscore the links between Labrador Sea processes, quantified in terms of deep convection, Labrador seawater production, or Labrador Sea density, and low frequency variability and predictability in the subpolar North Atlantic. And so the question is, how do we reconcile the new observations with our modeling results? And one answer is that model bias results in an overemphasis on lab sea processes. And the argument made in a couple papers demonstrating how biased models are in terms of their deep convection in the Labrador Sea. Another explanation could be that the key Labrador Sea density signals are not locally forced, but are in fact vectored in from the eastern subpolar gyre where they are generated. A third explanation could be that surface transformation and ventilation are not co-located. So while the eastern subpolar gyre is the region of maximum surface transformation, the Labrador Sea could very well be where deep waters are ventilated. And then a fourth explanation that I'm going to be focusing on is that the active role of the Labrador Sea is most apparent at longer decadal timescales. And so I'm going to present a new perspective on low-frequency AMOC mechanisms obtained from a long eddy resolving pre-industrial control simulation. So the simulations I'm going to be analyzing in this talk are from IHESP, and they're recently presented in an overview article in James led by Ping Chang. And what we have are two parallel pre-industrial control simulations, one at low resolution, nominal 1 degree, and the second at high resolution, which is a 10th degree ocean and sea ice coupled to 1/4 degree atmosphere and land. The forcing for both of these is 1850. They're both 500 years long, and my analysis will focus on the final 300 years. And I'm going to focus mainly on low frequency variability, so band pass filtered, low pass filtered with a 10 plus year period cutoff. So here's what these simulations look like in terms of winter deep convection. On the upper left here is the mean March mixed layer depth from the low resolution simulation. And then in the middle here is from the high resolution. And then we have an estimate from observations from the Argo data set on the right. And you can clearly see that the low resolution overcooks convection in the Labrador Sea. Much too extensive and deep. And the high resolution significantly improves on that, showing max amplitude and location of deep convection that corresponds quite well to what's observed. Shows a secondary maximum here in the Erminger Sea, which may be a bit stronger than observed, but these are the observations are quite limited, about 15 years. And then if we look at the low pass filtered variability, the low resolution showed this strange looking extension into the southeastern Labrador Sea that is not co-located with where the maximum mean deep convection is. In high resolution, this variability is much more commensurate with the mean convection, and in fact shows slightly higher variance in the Erminger Sea region than this region in the Jin Seas. So I think on this basis, we can feel confident that the high resolution has improved the realism of subpolar North Atlantic processes. I also want to point out some regions that I'll be referring to. The orange lines here, the OSNAP array lines interpolated to the model grids. I've got a Lab Sea region, a Western subpolar gyre, Eastern subpolar gyre, Erminger region, and a Jin Sea region. Arctic is way up here, but I'll mostly ignore that. So a second confirmation of the improvement in high resolution is shown in these panels, which directly compare the simulated overturning across the OSNAP arrays to the OSNAP observations, which are in red. The tops show the 21-month mean overturning profiles, and then the bottom show the 21-month standard deviation. For the simulations, these statistics are given in terms of 300-year mean statistic and then the min-max range of rolling 21-month window. So you can immediately see that the low-res excessive deep convection in the Lab Sea gives this very unrealistic peak overturning across OSNAP West that is far too large compared to the observed value of about 2 to 3 spherodrips. Here it's about 10. And we significantly improved that in high res with the reduced convection in the lab C. Now we're below 5 in the mean, and the range is starting to encompass the observations. There's still discrepancies. So it seems that in high res, we're still too strong compared to OSNAP, and particularly in the east and in the total overturning. And when we compare the 21-month variance, we see that OSNAP falls outside the min-max range from high res. So that's a little bit disappointing. The high res isn't completely compatible with the observations, but certainly much better than the low res. So now if we think about low frequency AMOC variability in density coordinates, I'm showing you the mean stream functions from low res and high res here. And then the color shading shows the low frequency standard deviation. In both of these, you see a maximum variance in the Labrador seawater layer, which is around 37 in sigma 2 units. It's extremely pronounced in low resolution, and it's much weaker in high res, but still evident as a maximum variance. And you can sort of get a hint of the propagation of variance from the deep layers into the less dense layers. I also want to point out this secondary band of high variance. This is in the light, warm North Atlantic current component of the overturning and density space. And we see that in both low and high resolution. So we have these twin lobes of high, low frequency variance. So to get at the regional drivers of AMOC, I'm going to use surface water mass transformation analysis, which many authors have used, and I don't have time to go through it in much depth, but suffice it to say that we can compute a surface forced overturn and stream function just from that surface density flux. And here I'm doing it based on monthly mean model outputs. And then the water mass formation is the convergence of this transformation. So if we look at the surface forced overturning north of 45 north in low res and high resolution, they have a lot of similar features. And if you break it down by region, you can see that the transformation from light into dense waters takes place successively in these different regions. So the subpolar gyre transforms relatively light, hands the baton to the Erminger Sea, and then the Jin Seas, and then finally the Labrador Sea is transforming into the densest water mass classes. And here you see that the Labrador Sea surface force transformation is very strong in low resolution. There's still a peak here in high resolution, but it's much lower than the transformation rates in the other regions. So this is a complicated plot, but I'd like to explain it. First, the top panels are all showing mean overturn and stream functions. And then the bottom panels all show the low pass filtered standard deviation. And this is all from high resolution. So you can see that in high resolution, the Labrador Sea plays a relatively minor role in the mean transformation of waters into lower limb AMOC waters, but it plays an outsized role in the formation, so the convergence into the Labrador Sea water mass class that's seen here. This blue curve is formation that's taking place within the Labrador Sea. And the low frequency variability is extremely pronounced in the Labrador seawater class, both for transformation and formation, and much of that variability is associated with buoyancy forcing in the Labrador Sea. And then if you compare the transformation variability to the actual overturn variability, you see this nice match. So that deep variance maximum really is associated with variance in the Labrador seawater layer. So if we look at the variability from high res in terms of this Hofmuller plot, this shows the AMOC stream function at 45 north as a function of time and density. And then at the bottom here is the deep Labrador seawater formed at the surface in the Labrador Sea. So first thing to point out is that large AMOC signals emanate from formation of deep Labrador seawater. and they propagate upward in density space. We can also see that surface water mass transformation lags the North Atlantic current spin up. So the North Atlantic current is way up here. And once that spins up, then we see a propagation of water mass transformation downward in density space. That's particularly pronounced in the eastern half of the gyre. And we also see some evidence of preconditioning. So this deep Labrador seawater formation anomaly seems to emanate from a prior water mass transformation anomaly. But I want to point out that the Labrador Sea is doing much of the heavy lifting in the tail end of this transformation. So this strong transformation anomaly that I've pointed out, some of it is coming from the Eastern Gyre, but most of it is associated with local forcing in the Labrador Sea. So this is my final plot. I just want to show you what this looks like in 4 dimensions. So if we do a lag composite on large AMOC anomalies at 45 north, what we find is the deep limb spins up first, and it's associated with deep convection in the Labrador Sea that expands out into the Erminger Sea. We get a thickness anomaly in the deep Labrador seawater layer, and we start to get corresponding anomalies in SSH. And so by the time we're at lag 0, this is fully developed with a strong thickness anomaly in the abyssal ocean that is resulting in a SSH anomaly of opposite sign. And so we can see how the coupling between the lower and upper limbs arises via this SSH gradient anomaly driven by deep Labrador seawater thickness anomalies. So to conclude, a high-resolution PI control simulation appears largely compatible with all the recent observational work arguing for the dominance of the eastern subpolar gyre. In low resolution, the diapicnal transformation is clearly too strong in the Labrador Sea, but the improved realism in high-res suggests it can provide plausible low-frequency context for observations. And despite low mean surface transformation in the Lab Sea, anomalous transformation and formation at the tail end of North Atlantic deepwater production, that is Labrador seawater, is implicated as a key pacemaker of the low-frequency AMOC variability. So preconditioning in the eastern subpolar gyre is important, but I've shown that local Lab Sea transformation is a critical element. There's evidence of a multi-decadal gyre mode with AMOC both driving and responding to surface transformation in the east. And at the very least, Labrador sea metrics appear to be good indicators of cumulative subpolar North Atlantic transformation. And then finally, AMOC in sigma space is driven from below, with the lower and upper limb coupling associated with coherent changes in Labrador sea thickness and SSH. And so it highlights the role of surface formation in AMOC dynamics, not just transformation. And the formation, I think, is a key to understanding North Atlantic decadal predictability. Sorry for going over.
You didn't. You're perfect. Questions for Steve? Dan.
Hi, Steve. Thanks for the talk. I was wondering if you looked at variability on timescales longer than multi-decadal, and I was also wondering if you could describe what the propagation of the deep water formation into the Erminger Sea from the Labrador, what that looks like, why it goes that way.
So this analysis does include all timescales longer than decadal. So I'm just filtering out the high frequency interannual variability. I'm including multi-decadal. And then the second question, the propagation into the Erminger Sea. Is this what your question relates to, sort of how?
Yep.
I guess I don't quite understand the question. It appears that initially stuff is happening in the Labrador Sea. So we've got deep convection and some limited convection in the Erminger Sea. And once we get some thickness anomaly in the Lab Sea, we perhaps that is propagating out of the Labrador Sea, or perhaps this is locally driven by this this deep convection in the Erminger Sea.
Yeah, okay, thanks. I guess I was just wondering why it went that way and not further into the Labrador Sea, for instance.
Good question. But I think this propagation out into the interior and along the western boundary is probably mostly related to the Labrador Sea force thickness anomaly.
Thanks.
More questions for Steve? I have a question, Steve. I mean, through this analysis, do you have a notion of why the low resolution model is having trouble in both the mean and the variability? You know, sort of look at, say, the bolus flux component of these overturnings, or can you see anything there that suggests that what might be going wrong?
So we've been looking at what could explain this big discrepancy in winter deep convection between low res and high res. And there are a couple thoughts. One is that in high res, you've got the West Greenland current rings that are, you can kind of see a footprint of them here with low mixed layer into the interior Labrador Sea. So that's a re-stratifying effect that's missing in Labrador in the low resolution. But then one of Ping Chang's students has also shown that there's some vertical eddy buoyancy flux that's very strong along the Labrador coast that would appear to also be a re-stratifying effect in high resolution that's missing in low resolution.
Okay. So the suggestion is that we are missing something in our parameterizations of the mesoscale.
That's the leading hypothesis, yes.
Okay. We got a couple more minutes if anyone else has a question. Bob.
Thanks, Steve. That was a nice talk. One of the things we found sometimes is that the sea ice extent can play a big role in where the deep convection occurs. In some cases, sea ice expanding over the Labrador Sea seems to be particularly problematic. Was the sea ice extent in these simulations such that you think you can rule out any issues related to sea ice extent as explaining some of the differences either between the models or between the models and the observations?
Yeah, that's a bit of a chicken and egg problem, right? Because the deep convection is bringing up warm water and that tends to erode the sea ice edge. I think it's certainly the case that in low resolution, the sea ice edge has retreated too far, as you can tell by this location of the maximum here. But why that's the case, why there's this positive feedback between deep convection and sea ice retreat is kind of the question we don't have an answer to. And that relates to Frank's question. You know, I think it's missing parameterizations or ineffective parameterizations that are particularly problematic in this region. So one point that I failed to make is that even though this is clearly unrealistic in low resolution, and the variance associated with this deep Labrador seawater production is too high, many of the same elements explain AMOC variability in these two simulations. It's just stronger in low resolution.
Tony?
Hi, Steve. I've also been looking at this issue also within our data assimilation and in the reanalysis, and particularly focusing on the Argo period. And since 2014, which had a deep convection event, and I've been trying to follow that toward the AMOC, and soon I think I should be able to produce a figure just like yours during the Argo era for that event. So stay tuned.
Yeah, I'm also interested in looking at this in our OMWG simulations. But many of the same arguments still hold, that much of the historical AMOC spin-up can be related to Labrador Sea convection, even in high resolution, at least in our simulations.
Yes, right.
Okay, great. Thanks, Steve. Next, we have Hailu Kong from University of Chicago. Is Hailu here? There we go.
Can people see my screen now?
Yeah, yeah, you're still in sort of the edit mode there, not full
Yeah.
screen.
Yes, sure. Is it better now?
There you go. Great.
Cool. Great. All right. Thanks everybody for coming. In this talk, I'm going to share some of my PhD dissertation research on the impact of topography and eddy parameterization on the simulated Southern Ocean circulation response to changes in surface wind stress. The work has been out in GPO this last December, and you're welcome to check it out. So a broad background of this work is the surface wind stress intensification during the past few decades, as is shown in this diagram, where you can see that different reanalysis data set show that like prevalently that all the surface wind stresses products show an intensified surface wind stress for the past few decades. Furthermore, climate projections show that in the coming decades, the surface wind stress will continue to increase. So a natural question for us as oceanographers to ask is, how would Southern Ocean circulation respond to this change in surface wind stress? So specifically in this work, I'm trying to stress 3 questions. The first one is, how does Southern Ocean circulation respond to surface wind stress changes? Second is, specifically, I'm going looking at 2 components of Southern Ocean circulation, being that the ACC and the overturning circulation. Especially, I'm going to look at the upper cell of the overturning circulation. Second question is, how may topography affect this response at all? The third one is, can cost resolution simulations, especially with parameterized mesoscale eddies, capture this response, as well as the role of topography at all? To address these questions, we designed 2 idealized configurations of Southern Ocean by MOB6, which I showed here. So on the left is the flat bottom channel case. On the right is the flat bottom channel plus some topography. Specifically, you have this Scotia arch surrounding the Drake Passage here, as well as the continental block mimics the South America. Okay, for surface boundary condition, here for wind, the black curve shows the state of current climate, and I'm gonna vary that to give you 4 different wind stresses apart from the current climatology. Oops, sorry. And for buoyancy, I'm restoring the surface buoyancy towards this linear trend, which is pretty close to what we observe. So we are using MOB6 in isopycnal coordinate, which has 30 layers. So for each of these different combinations of topography and wind stresses, I'm gonna run 1 high resolution simulation where mesoscale eddies are largely resolved, as well as a couple of different 1-degree parameterized simulations where I configure different parameterization schemes and to compare them against this high resolution simulation, which is taken as truth. Okay. The real tricky part of this kind of configuration lies in its northern boundary condition, because it's not really closed. And so we have introduced 2 types of different northern boundary conditions. The first one, we use a sponge layer in the north to restore the stratification so that it mimics the diabatic water mass conversion that's taking place in the basin that's to the north of Southern Ocean. This type of configuration allows the existence of a non-trivial residual overturning circulation. Therefore, it can be used to study the response of MOC. However, the problem of this configuration is that together with surface restoring buoyancy condition, they largely constrain the degree of freedom of the change in the isopycnal structure. Therefore, it's not good to study the ACC transport using this configuration, since the ACC relies largely on your isopycnal structure. To remedy that, we introduce a second type of northern boundary condition, which is simply a no flux boundary condition, so that there's no water mass transformations across the isopycnos at this boundary. This boundary condition allows the free adjustment of isopycnal structure here, which enables the ACC to respond freely, so that it can be used to study the response of the ACC. So in the rest of the talk, I'll be comparing the results from these two types of boundary conditions. So the parameterizations I am testing in this work are, first, I'm testing a group of constant GM diffusivity cases ranging from 700 meters squared per second all the way to 0 with increment or decrement of 100 meters squared per second. Also, I tested the classical Wisbeck scheme, where they parameterize the diffusivity as a product of this constant of proportionality alpha times the length scale square times the vertically integrated product of isopycnal slope times the vertical stratification. I also test the Mickey scheme. I believe people have been hearing this once again in this workshop, where we're using the form that's proposed by Janssen et al., where the diffusivity is parameterized as a product of square root of eddy kinetic energy times some length scale, where there's a separate prognostic equation to predict the evolution of subgrid scale eddy kinetic energy. On top of that, we also test in different scale called the T-Mickey, which is just the topographic Mickey, where we use topographic beta in the place of traditional beta, which is the gradient of Coriolis parameter in Ryan scale. Specifically, this is the form of the effective beta we're taking. So apart from this traditional form of beta, we also introduce this contribution from bottom topography in changing the gradient of vorticity. Also, we tested T-Mickey with two types of differently vertically varied GM diffusivity. The first one is what we call the equi-BT, which is equal to use in an equivalent Bertrobik structure. I'm sorry, an equivalent Bertrobik structure for GM diffusivity, where EMOP6 is simply by turning this parameter on. And alternatively, we use this Ferrari et al. Scheme, which instead solves the vertical elliptical equation for eddy induced Mach. So these are what I'm going to do. So first, I'll show you the results from two baseline comparisons. So by baseline, I mean I'm going to use the topography case. So for now, neglecting the flat bottom case, as well as I'm going to only show the results with reference wind stress, that is of current climate. Okay, and the two baseline comparisons are just the one with sponge versus the one without sponge. So for the sponge case, here on the right panel, I show you the result, where on the upper panel is the Mach, both for the upper cell in red and lower cell in blue. Actually, it's the negative value of lower cell since it's negative, as a function of different parameterizations as here. And the two horizontal lines denote the Mach from the eddy resolving simulation. In the lower panel, I show you the interface height error epsilon, defined to quantify the difference between your interface height from the coarse resolution simulation versus the high resolution simulation. So the larger interface height error is, the more deviated your interface height from the coarse resolution is from your high resolution. Okay. So from this comparison, we can see first, if you are using a constant GM diffusivity, which is small, that can reasonably get both the upper and lower cell Mach correctly. So that's for a constant GM. However, a constant but large GM will definitely miss the lower cell significantly. Okay. Second is that it seems that by introducing this vertical structure for GM diffusivity or for the eddy induced Mach, does not really improve the simulation of both the upper cell Mach and the lower cell Mach, especially the upper cell Mach, which is the emphasis of this work. Also, as you can see here, that by introducing this vertical structure doesn't necessarily lead to a smaller interface height error. Last, as you can see, our T-Mickey or topographic Mickey is performing the best, both in terms of getting the upper and lower cell Mach correct, as well as getting the smallest error. Okay, so that's the result from this first baseline comparison with a sponge. Now, what if we do not have a sponge? Again, similar panels for upper panel for the ACC, lower panel for the interface height error epsilon. As we can see now, this time, if you are using a constant GM diffusivity, which gave you a reasonable reproduction of Mach in the previous slide, now gives you a pretty bad representation of the ACC transport, and which also gives you a large error in the interface height. And these two are comparable. So we can see that this time a small kappa GM won't work. And it's actually an intermediate value for kappa GM that works. Also, we still can see that the TMIKI here also performs the best. And I need to mention that I am not running the simulation with vertically varying GM in this case, since it turned out it didn't work that well from the previous slide. So to first summarize the results I've got so far, first, there's just simply no optimal value for constant GM diffusivity to capture both the Mach and ACC transport correct. Second is our topographically modulated Mickey seems to be the best, at least in these two baseline comparisons. Okay, now what if I'm gonna vary surface wind stress? First, I show you the results in terms of the ACC transport. So here, as you can see, it's the flat bottom case of ACC transport as a function of different surface wind stress. And the first thing I would point out to you is that the transport from the high resolution simulation is pretty insensitive with wind stress changes, which is consistent with previous findings. Unfortunately, this insensitivity is not captured by all the cost resolution simulations I've tested here. And this turns out to be because all the cost resolution simulations are underestimating significantly the transient eddies, reflected as the underestimated value of GM diffusivity, so that their asymptoticals tend to be much steeper than the eddy resolving simulation, which gives you a much stronger and more sensitive ACC transport. In the case with topography, however, things are a bit different. First, again, we noticed that there's this still pretty insensitive response of high resolution simulation, as you can see from the black crosses. And also, I'd like to point out to you that this insensitivity is much higher than here, since if you notice the y-axis range differ by an order of magnitude. So that with topography, you have a very insensitive response of ACC transport. This is also consistent with previous findings. But more importantly, as you can see here, that all the eddy non-eddying simulations with parameterized mesoscale eddies can reasonably good capture this sensitivity of ACC once you have topography, as opposed to the case in flat bottom. And it turns out this is not because they're doing a perfect job in capturing the GM diffusivity, which they can't, because especially for these two cases with constant GM, you just cannot get a changing GM diffusivity with wind stress. However, this is largely because these parameterized simulations are able to more or less resolve the large-scale stationary eddies, which turn out to be dominating over the transient eddies. And in together, these two parts of eddies will give you a reasonable response of isobutane structure, which denote a reasonable response of the ACC transport. Okay, and now how about the Mach? For the Mach, first let's look at the high resolution simulations. So all this can be trusted. So here I show you the Mach sensitivity as a function of surface wind stress for the upper cell only. First, as a reference, I also plot what's denoted by this wind-driven Mach. So this is the Ekman-driven Mach without any change in the sensitivity. Oops, sorry, what's going on? Without any mitigation by the eddy-induced Mach. Okay, and we notice that first, if you are in the flat bottom case, without topography, the transient eddies will play some role to bring down your sensitivity of Mach, which is called the eddy compensation effect by previous literature. However, if you have topography, this suppression effect will be much more robust and gives you a much less sensitive response of Mach to wind stress changes. So the next question is to ask, can the parameterized simulations capture both of these suppression effects? The answer is yes, but for different reasons. First, if we look at the topography case first, you can see here that different parameterized simulations capture reasonably well the sensitivity of Mach as a function of surface wind stress. And further analysis shows that this is because the parameterized simulations get the Mach correct for the correct reason. By that I mean they get both this combined diffusivity, which is the sum of GM diffusivity plus stationary diffusivity. Since in this case, this is really what matters for rectifying your asymptotic slope, as well as your asymptotic slope correct. So specifically, if you look at this model panel plot on the upper left, I show you the combined GM plus stationary eddy diffusivity as a function of surface wind stress. As you can see, despite slight underestimate of the combined diffusivity, all the parameterized simulations give a reasonable representation of the combined diffusivity. Okay, and all the rest of the panels, I show you the zonal mean asymptotic structure from the different configurations. So this one's high resolution, the other four are from the low resolution simulations. And I showed you the color in red is the high wind stress case and black in low wind stress case. And as you can see, all the simulations here show that despite a tripling of surface wind stress, you still see a relatively insensitive response of your asymptotic structure. And this insensitivity is well captured by all the parameterized simulations. Therefore, since the eddy-induced Mach is can be expressed as the multiplication of eddy diffusivity times the asymptotic slope, a realistic capturing of diffusivity as well as a realistic capturing of the slope will definitely give you a realistic reproduction of your eddy-induced Mach, and therefore a realistically reproduced residual Mach. And that's for the topography case, so that the parameterized ones are good. However, if you are in the flat bottom case, things are a bit different. Still, you see this almost perfect reproduction of Mach sensitivity as a function of surface wind stress in the coarse resolution simulations. But unfortunately, this perfect result is due to a weird compensating effect. By that I mean, in the coarse resolution simulations, both the GM diffusivity as well as the asymptotic structure are off. However, their errors seem to compensate each other so as to give you a correct response in the eddy-induced Mach. So as here, if you are, in fact, in this case, the in the parameterized simulations, all the diffusivity are too insensitive, and therefore your slopes are too sensitive. But together, they give you a reasonably good sensitivity of the eddy-induced Mach. Specifically, I show you again the similar kind of plot. As you can see, since we're in the flat bottom case, there's just no stationary eddies. So I'm only showing you the GM diffusivity this time. And as you can see, all the parameterized simulations are significantly underestimating your GM diffusivity. Not to mention these two constant GM cases where your diffusivity by definition doesn't change at all across wind stresses. And for the interface height error, sorry, for the zonal mean interface height changes, as you can see for the high resolution simulation cases, it's still relatively insensitive to surface wind changes, but it's super sensitive in these parameterized simulations. And as I just introduced, the error of the both components just compensate each other so as to perfectly give you a good result for the residual Mach. However, the reason for why there should be such a perfect compensating, we just do not understand. So to summarize my work, first, we compared two baseline comparisons and a reference wind stress with topography, and we find that first, there's just no optimal value for a constant GM diffusivity. Second, we find that introducing a vertically varying GM diffusivity or eddy-induced Mach seems not to be contributing much to an improved eddy parameterization. Third, we find that our T-Mickey performs the best, at least in these two baseline comparisons. Second part, as we change surface wind stress, we find that first, both the ACC and MOC remain relatively insensitive to wind stress changes. And it turns out that topography significantly suppresses this insensitivity. And the reason is that stationary eddies turn to dominate over transient eddies in bringing down the sensitivity of both ACC and MOC. And it turns out these 1 degree resolution simulations reasonably capture the suppression of responses of both the ACC and MOC in the presence of topography, largely because stationary eddies can be resolved in these simulations, which dominate over the transient eddies, and they somehow do not get the result correctly in the flat bottom cases in terms of capturing the ACC. And for the MOC, they get the correct response, but for the wrong reason. So this should give us some cautious confidence in our climate projection of what's going on in Southern Ocean circulation, at least in the coming decades or even longer time scales. So with that, I'll conclude my talk and take questions. Thanks.
Thank you, Hailu. Takaya had his hand up first and I accidentally lowered it. So Takaya, why don't you go ahead?
Oh, okay. Well, yeah, thanks for giving me the opportunity. Thanks for the talk. I thought it was really cool stuff. I just had one quick question. So when you compare, you have like, I think it was like the first half of the talk where you compare all these parameterizations. Yeah, that one. And then you have the next slide where you don't have the sponge.
Yes.
And then I think you mentioned that you didn't test like cases where you allow KGM to have a vertical structure.
Right.
But did you actually test that for the no sponge case, or?
I didn't test that. So I just test that case for this sponge case, actually with far more parameterizations as you see here. I varied the parameters, and despite all that effort, it doesn't really change the result, improve the result. So I actually didn't implement these two for the non-sponge case.
Okay, do you think, well, you also said it in your introduction, but by introducing the sponge, you kind of limit the like degrees of freedom. Do you think there would be any like differences in the performance for the no sponge case if you allowed vertically varying KGM?
Not really, because here all the comparisons are an apple-to-apple comparison. By that I mean all these have sponge, right? And for this, if suppose I do have this vertically varying GM diffusivity, and that, as I mentioned, can have more degree of freedom in terms of adjusting your observation structure. But that is also the case for other parameterizations, right? So I see no reason why introducing a structure here, vertical structure here, might help much in getting the best answer to the ACC transport as well as epsilon.
Okay, yeah, thanks.
No problem.
Okay, Tony Rosati, did you have a question?
I think that's from last time.
Okay. Gokhan.
Yeah, I had a comment and a question, and the comment relates back to the previous one. I'm a bit surprised that you eliminated the vertical variation in the coefficient, because that is a tunable thing. You can essentially adjust the coefficient magnitude. And more importantly, any kind of spatially varying coefficient specification or prescription, such as the vertically varying one, can respond actually to the surface forcing as well as to the stratification. And I would have expected more of its impact in your later simulations with increased wind stress. You have shown that thing in several publications. But my question actually relates to your control, the truth. I see, if I understand your plot correctly, the strength of the overturning circulation, I'm assuming that is the total, increases with increased wind stress. I don't see any compensation. Why don't you see any compensation in your, you should, one of the plots, that the overturning function. I was expecting, I mean, again, there are publications on that. With increased wind stress, there is compensation, and then the total MOC southern overturning circulation does not necessarily increase. And that's why I'm a bit surprised at your truth.
Actually, I think the term eddy compensation is used to describe the fact that, or the hypothesis that your change in your wind-driven circulation will be compensated, but not necessarily perfectly by the eddy-induced Mach.
Yeah, but in this case, you almost have a linear relationship. I fail to see sort of at least partial compensation.
I mean, the difference between the wind-driven Mach and the actual residual Mach is the part that's compensated by the eddy-induced Mach, right?
Okay, maybe I misunderstood. So there is compensation after all.
Yes. Also, another thing I need to point out is that the wind stress range I performed here is relatively limited compared to other possible idealized studies. For example, people can have a factor of 10 in terms of wind stress changes, which may give you some different answers rather than this linear trend.
Okay.
That's another possibility, right?
Steve Griffiths.
Thanks for the talk. I'm sorry to go back to previous two questions, but if you can go to the original sensitivity study, yeah.
Mm-hmm.
For the vertical structure, you said that you're testing the vertical structure with the Miki and the T-Miki and the equivalent barotropic, but my understanding in the MOM6 code that those are still depth independent diffusivities. They're just depth integrated, right? It's a depth integrated eddy kinetic energy equation. So it's an
yes.
And VSpec is also, so you're not really testing the depth dependent diffusivity in those schemes.
Right. So the way my understanding is that yes, Miki and T-Miki are both depth independent. It's vertically integrated. Yes, as you mentioned. However, the way that equivalent barotropic structure works is to superimpose a vertical profile to the diffusivity that's predicted by either Miki or T-Miki, so that what's actually entered into the GM scheme is a vertically varying profile.
Mm-hmm.
Yeah. So
to follow up, so to follow up,
mm-hmm.
I mean, I think I'm still not convinced. I think you didn't do a sufficient study of the kappa Z, but that's, I mean, there's a whole lot of stuff out there that I'm not being too judgmental. I mean, there's too much to study as part of the CPT. The Ferrari scheme, you seem to drop, and I'm just kind of curious to know, was it a numerical problem that caused you to drop it, or you just felt like you needed to weed out the ones that you didn't like, or what was the problem with that?
As I mentioned, it's not capturing the upper cell correctly here. And we tried with different parameters for this game, and none of them gave me a satisfactory result. Mm-hmm. So in further comparison, I just neglect the vertical variations altogether. Yes.
Okay.
Okay. Great. Thanks again. I think we need to move on.
All right. Thank you.
Next up is Lucas Lorindo from NCAR.
Okay. Can you see my slides?
Yep.
Okay. Hi, everyone. My name is Lucas. I'm a postdoc at NCAR. I'm going to talk about my current research, which investigates the role of ocean variability in air-sea interactions as resolved by climate model simulations. So it is now well known that mesoscale ocean variability can produce SST anomalies that are large enough and persistent enough to have an impact on the surface turbulent fluxes. And this contrasts with the traditional view in climate dynamics that SST variability mostly driven by the atmosphere. And there is increasing evidence that these ocean-driven coupling mechanisms can play active roles in both weather and climate. However, the ambient conditions in the ocean and the atmosphere that allow the ocean influence to prevail are still poorly constrained, and this study aims to elucidate in what conditions the ocean can prevail over the atmosphere. Here we use CESM simulations produced by the International Laboratory for High Resolution Earth System Prediction, IHASP, which is a collaboration between NCAR, Texas A&M, and the QNLM Laboratory in China. Here I'm going to contrast results from simulations run at resolving and at parameterized ocean resolutions. I'm going to refer to them as high resolution HR and low resolution LR. I specifically use SST and turbulent heat flux data from quite long pre-industrial runs, 250 years for HR and 500 years for LR. However, I did not have access to some heat budget terms until recently, the reason for which some of the results that I'm going to show you are computed using data from shorter high-res mean runs. I'm currently updating my results using data only from the PI runs. These global maps show the ratio between SST variance in HR and in the LR control runs, and between the turbulent heat flux variance in each simulation. Both maps shows that HR resolves much larger variances in the exotropics, most noticeably at energetic ocean current systems. Note that the current color scale here is logarithmic, meaning that a value of 1 indicates that HR has 10 times more variance than LR. These maps are also very similar to each other. This is consistent with the interpretation that in HR, SST variability driven by the ocean processes is forcing a response in the turbulent heat fluxes. Here, I'm using spectral methods to evaluate how the excessive SST and THF variance in HR is distributed across different spatial scales. These results refer to a zonal section of the Arguelles return current, but they are emblematic of what is observed over much of the exotropics. NOAA shows that the power spectral density of SST and THF resolved in HR and LR, computed as a function of the zonal wave number. It also shows observational estimates from the J of Furrow product. All data sets, they show similar power spectral density at scales larger than about 2,000 kilometers. And as you go towards smaller scales, you can see that the power remains high in observations and in HR, but it rapidly drops in LR. Panel B shows the coherency between SST and THF. Coherency is a statistic that measures how any two signals are related with each other, being 0 if the signals are unrelated, and it is 1 if they are perfectly matched. In HR and OBS, the coherency increases to values close to 1 over scales smaller than about 2,000 kilometers, meaning that SST and THF vary together over these scales. And it seems that LR even tries to do something similar, but the signal is much weaker. This next slide shows the same spectral quantities as before, but computed as a function of frequency. Here, these estimates are obtained using data filtered in space to isolate scales that are smaller than 1,000 kilometers. So we are really in that regime where SST vary together with THF. NOAA shows the SST and THF power spectral density as a function of frequency. Again, it reveals that HR and observations have much more power than LR. Note that the power progressively increases towards lower frequencies until stabilizing at about 500 days. Then continue with about the same power until the limit of the analysis, which is 130 years for HR and 13 years in observations. We can call these a red power spectrum because they show more power over low frequencies. In the LR, the power spectrum is also red for SST, but the THF power spectrum shows nearly the same power at all frequencies. So you can call it a white spectrum. Finally, panel B shows the coherence between SST and THF and reveal that these quantities are highly coherent in HR and observations, but not in LR. These results suggest that ocean phenomena can influence SST and THF at rather large spatial scales and over very long time scales. To try to explain these characteristics, I'm using an idealized model for the upper ocean temperature evolution. This formulation was proposed by Frank New et al. 1998, and its use in this study was recommended by Dr. Luane Thompson from the University of Washington. The model is forced by the NA and NO signals, which represent the action of intrinsic variability in both the ocean and the atmosphere. Sigma A and sigma O are their standard deviations. This model is composed by a turbulent heat flux term, which includes the atmospheric forcing, a radiative damping term, and Luane extended it to include the forcing by ocean process represented by NO, and I further include the diffusion term. I use this model to obtain analytical solutions for the power spectral density of the upper ocean temperature, G11 here, and for turbulent heat fluxes, G22. Note that both solutions depend on NO and NA. And on their variances, sigma O squared and sigma A squared. Previous studies used white noise to represent NO and NA, also prescribing how much variance there is in each. But here I wanted to use signals with a realistic power spectral density distributions in both frequency and zonal wave number domains. The idea is to verify if the presence of structure in the noise could give rise to the observed scale dependency of Earth interactions. And to this end, I decided to use real geophysical data from the climate model simulations. I chose to use 2-meter height humidity for NA because we found that it was not strongly correlated with oceanic quantities such as ST, and ocean heat flux convergence for NO, which many recent studies are showing that it is the main mechanism driving the mesoscale SST variability. Essentially, I divide this data series by their standard deviations to make them non-dimensional. I Fourier transform them, and then plug the resulting spectra in the analytical solutions that I showed before. The figure in this slide shows the power spectral density of NO and NA signals as a function of zonal wave number frequency. Note that they show structure in spectral space. While the atmospheric signal, NOA here, is approximately white in frequency space, it's red in zonal wave number space, with much more power over large spatial scales. In contrast, the ocean signal shows enhanced power following the dispersion relation for oceanic Rossby waves, represented here by these black lines. We also have to define how much variance there is in each forcing signal. I did this by least square fitting the analytical solutions to the temperature and THF power spectrum resolved by the climate model simulations. And okay, so here, panel A shows the power spectral density of the upper 50-meter temperature for 40 South of the Pacific from the high resolution run, while panel B shows the best fit estimate from that I obtained from the idealized model. They are visually very similar to each other. Panel C shows the component of the theoretical solution that depends on NO, while panel D shows the component that depends on NA. The bottom panels E and F shows the ratio of each component relative to the total power spectral density in B. In panels E and F, warm colors here indicate that the component is dominant. These results indicate that the ocean drives most of the temperature variability over scales smaller than about 2,000 to 1,000 kilometers, while the atmosphere dominates over large spatial scales. Now, in these slides, it shows the corresponding results for the low resolution run. Please note in panel A that the power is much less than HR of a scale smaller than about 1,000 kilometers, most noticeably along the dispersion relation for Rossby waves. Let me flip back and forth just so to emphasize the differences. Okay, most of the difference come from, compare both figures, most of the difference come from the ocean component, shown here in panel C. The atmospheric component does not really change significantly. Now, this slide shows the corresponding figure for turbulent heat fluxes in high resolution. We see, looking at panels E and F, we see that the ocean now dominates a larger area of the spectrum, and the atmosphere seems important only over large spatial scales and time scales shorter than about 3 years. And here are the results for low resolution. Again, the power decreases over spatial scales smaller than about 1,000 kilometers relative to HR, near the most noticeably near the Rossby wave dispersion relation. And despite the reduction in power, panels E and F indicates that the ocean influence in THF is still large over a wide range of spatial temporal scales, even though we are looking at the low resolution one. Okay, In this slide, I'm showing the same spectral estimates that I showed before, but integrated over the frequencies to obtain the power spectrum as a function of zonal wave number in panels A and C, and over the integrated over the zonal wave numbers to obtain the frequency power spectrum in panels B and D. The gray lines here are the power spectrum computed using CESM data, while the blue and red lines are best fit estimates of the ocean-driven and atmosphere-driven components. The black line is their sum. Please note that the power in the ocean component is much larger in high resolution than in low resolution, while the power in the atmosphere component is very similar between both simulations. Looking just at panels A and C, we see that the atmosphere-driven component prevails over large spatial scales. However, its power decreases steeply towards smaller scales, characteristic that allows the ocean-driven component to ocean-driven temperature modulation to prevail. Now at panel B, the ocean component in HR dominates the temperature variability of this period shorter than about 1,000 days, while in D, for the low resolution, the atmosphere dominates over the entire frequency range. Something that I think it's interesting, note that the ocean and atmosphere processes both drive a red spectrum temperature response with more power over low frequencies. For the atmospheric component, this response is compatible with the null hypothesis described by Frank New and Hassman, which states that stochastic forcing by the atmosphere drives a low frequency oscillations in SST. Our results here suggest that the same occurs in response to ocean forcing. According to the analytical solution shown here, the reddening of the spectrum occurs because the functions C and D, they are both inversely proportional to frequency, meaning that their magnitudes are going to increase towards lower frequencies. So throwing out more energy over the low frequencies. Okay, these are the corresponding estimates for THF. AC shows the same spatial dependency of the ocean and atmosphere-driven components that we saw for the temperature spectral estimates. However, panels B and D, they indicate that for both HR and LR, the atmosphere dominates the HF variability at the high frequencies, while the ocean dominates over low frequencies. Here, the ocean-driven response component also shows a red spectrum, which occurs because the functional E in the analytical solution is also inversely proportional to frequency. In contrast, the atmosphere-driven response is actually blue with more power over low frequencies. This occurs because the magnitude of function F actually decreases towards low frequencies. Okay, in a summary, we use the spectral methods to determine which scales ocean variability can influence the ARC coupling characteristics in climate model simulations. And we found that the resolved ocean variability in HR induced a much larger SST and THF variability relative to LR over spatial scales between 50 kilometers and 2,000 kilometers, and over time scales between 2 months to multi-decadal. Next, we attempted to interpret these characteristics using an idealized model for the upper ocean temperature evolution. And the results of this analysis suggest that the power spectral densities of the temperature and THF can be explained from the combination of intrinsic variability in the ocean and the atmosphere. We concluded that in wave number space, the ocean variability in HR prevails over scales smaller than 1,000 kilometers because over these scales, the atmosphere-driven modulation, it becomes weaker towards higher wave numbers, while coinciding with a strong ocean-driven modulation. In frequency space, we found that ocean variability produces a red spectrum response in temperature, a mechanism that seems analogous to that induced by the atmosphere. And the red spectrum response, this red spectrum response by ocean forcing is also mirrored in turbulent fluxes. In contrast with the atmosphere-driven response, which shows more power over high frequencies, thus driving a blue spectrum. And we found that in both high resolution and low resolution, this characteristic makes the atmosphere dominates the THF variability at high frequencies, while the ocean dominates at over low frequencies. Yeah, that's all I had. Thank you very much for listening.
Thanks, Lucas. Questions for Lucas? Oh, I saw a hand. Or Dan.
Hi, Lucas. Thanks a lot. That's really cool work. I guess I was wondering if you could talk a little bit more about how you think about atmosphere versus ocean noise, especially when you're pulling them from geophysical data, because we might expect these things to be related to one another.
I think the main point that I try to make, like, I think the fact that you have a coupled simulation will change the variability via feedbacks. But the point that I try to make is that this variability in the ocean atmosphere, it's not purely white. You know, you have structure in the noise. And what I'm trying to show here is that the presence of structure can actually explain these some characteristics of the spectrum. Can explain this scale dependency of RC interactions. And show some what I think interesting structure. So, like, if you assume any kind of noise in the ocean component and plug it into this formulation, you will have a red spectrum response. And also, the same goes for when you look at THF. Yeah.
Okay. Other questions for Lucas? Okay, thanks, Lucas. We're a little ahead of schedule, but we'll press on.
Thank you.
Next up is Jan-Erik Tesdal from Princeton.
Yes, hello. Make sure that you see my slide.
Yep.
Great. All right. So, yeah, this is my first time at the working group meeting. I'm excited to show some results that I worked on, part of my postdoc that I started a couple months ago at GFDL and Princeton, working with Graham McGilchrist, John Cresting, and Stephen Griffiths. And the talk is about a diagnostic tool that we've developed looking at the spatial temporal water mass transformation in a consistent way across models. So this is part of a larger project that I wanted to mention here, which is focused on developing metrics, also looking at ocean traces, transient ocean traces, as well as water mass transformation to better understand ocean ventilation, heat, and carbon uptake, and to improve our assessment and development of ocean climate models and reduce uncertainty in future climate projection. This is a cooperation we have with PCMDI and NCAR, and it's a DOE-funded project. So before I start getting into the presentation, I wanted to give credit to that really set the groundwork for this tool, and that is Graham, that I mentioned before, who plays an integral part, and he basically already worked on all these calculations, water mass transformations in WAM6, and I'm basically just using his knowledge and code to work it into a more self-consistent package. And that package is really built up on this wealth of Python-based open source software like Xarray and Dask, and especially the XGCM package that Ryan Abernathy developed, and also Julius Pusecki works on as part of the Pangeo project. There is an important package within that tool. Without that, this tool wouldn't be possible. Okay, so for the talk, I'll give a quick introduction about water mass transformation, and then we'll tell you about how we envision the workflow of this tool in a model analysis, and then I'll give you a few examples what we can already do with the tool and what we plan to do. So water mass transformation is essentially a different perspective of the ocean, where we, instead of looking at the coordinate, like in terms of coordinates and depth space, we define water masses, right? So we have layers, and then look at the transformation of water between those layers. This is nothing new. It's been around for many decades, but has been recently more generalized by Groskamp in 2019, that we also adopt here. So in general, you can define a scalar lambda that can represent a tracer, such as temperature or what have you, as well as buoyancy density. And then transformation is really the transport of water across the lambda isosurface. And whenever we have a non-zero material change in lambda, and which we denote here as lambda dot. And by convention, we have positive. This G transformation term is positive, means that we have water moving to larger lambda classes. So for example, density, water moves to denser water masses. So a nice illustration that Graham gave me, I think, is quickly kind of illustrates what water mass transformation is. So here now lambda is gamma, the neutral density. We have a contour of gamma, and so you have transformation occurring across that contour due to the non-zero tendency term due to density fluxes in this case. So you have cooling or freshening at the surface. You can have, and that then represents a transport of water across the density isosurface, isopycnal. And same, you have mixing in the interiors that then you have also represents an interior transformation term. And that's just showing mass budget, that you have change in mass in that layer equals the transformation and the overturning and the latitude. But most importantly, we can calculate the G term by this formula that I'm not going to derive, but it's basically we can use this to derive G. And the key in this integrand, which is our material change. So in this case, it's the local density tendency in the general framework, which is our lambda dot. So for everyone who's interested, I provide here, I recommend you check out Graham's tutorial, and where he shows how you can do the water mass transformation in MOM6, where he also goes into the details of how we calculate G. But just to keep in mind here is just the key is really we're binning contributions of this material change into the lambda classes. And so how do we calculate lambda dot? So how we focus on the process method, that means for the total material change, we have a sum of tendencies for different processes that are largely categorized by the interior that I showed previously in the drawing, interior mixing, plus the surface boundary forcing. And this complete, we call full 3D water mass transformation, but we also acknowledge that a lot of work has been mostly focused on the surface boundary, which we call surface water mass transformation. And ideally, we really want is the full picture, we want both tendencies in interior and surface, or the boundary. And this requires fully 3D diagnostic output, which we acknowledge might, especially when you think about multimodal analysis, a challenge. So we also worked on to handle surface water mass transformation by just using surface fluxes, which are just 2D surface fluxes. And for density, for example, we would need then flux fields of heat, fresh water, and salt. So for example, this is when the Seymour naming would be these three fields. And the last part, before I move to the next section, is that besides this G term, which is kind of this traditional view of water mass transformation, where you don't care really about the space, the coordinate system, we want to retain the spatial information by picking for a particular ISO value of lambda, have the spatiotemporal field of transformation that we then can basically map the transformation on that isosurface lambda I, and then map where transformation occurs for that particular lambda value. And that's also nothing new. A number of studies already have done that, but it was important for us to also use that tool to be able to have the spatial information. And I'm gonna present, have two that I'm putting here an underline that I show some examples where we compare their results with what we did. So in terms of workflow, so this is just showing how we imagine if you want to do model analysis, do water mass transformation analysis with your model in, let's say, a Jupyter notebook. So the first what you do is you read your model output. So this is independent of our package that you have either from disk, or now you can also have capability to directly load it from the cloud with intake ECM. And you have basically end up with a data set of flux and tendency as well as grid information. And then we think that we need some kind of pre-processing because the namings are different for the variables as well as coordinates that we then feed into our package that we're developing. And so we have two classes of functions. With this first the 3D water mass transformation using 3D tendencies, as well as surface water mass transformation with just surface fluxes. And this is where XGCM is very important, and basically provides us with the tools to do these calculations. And two outputs we have, like in general, is the integrated form that I mentioned, the G term, where we it's the most familiar of water mass transformation, where you just have this is just a sketch, so I'll just give you a visual. So we have just transformation across lambda, and then also a map where for a particular lambda we can map where transformation occurs. And this is then a transformation per area. So for example, you have Sverdrup in this axis, and here's a Sverdrup per square meter. Okay, so for the rest of the remainder of the talk, I just give you some examples just to illustrate how the capability of the tool. So we've picked a few papers, mostly observational work, that presented water mass transformation. So for the global picture, we found Hoey and Chaya presented the climatology of water mass transformation, where they show this picture. And we're using now the GFDL-CM4 model to use the tool to show what the output we get. So this is the same output with the surface fields. And we can also decompose it, the total, with the haline and the thermal part, and we can see consistent picture of the density. So this is now in sigma space of density anomaly, potential density, and we see that at higher values we get densification, so denser water moves to denser water classes, and lower density is where there's more lightening of water. So this is consistent with this overall idea in the global picture. And so this is the surface water mass transformation. In terms of the full 3D water mass transformation, we looked at Gross-Campbell actually used observations where they show where they have the represented boundary forcing and mixing term. And here we have also these output. So here in blue we have the boundary forcing, in orange the interior, the total interior mixing. Black is the same as I showed in the previous slide, the surface. And here we see clear differences. So there is overall a general agreement that we have where the overall pattern, but there are clear differences in terms of magnitude and the position of the classes. Also, this is a neutral density. Right now, I'm missing this as an option for lambda. So right now it's just sigma for density. And the key point here is really is basically underlying data. So for full 3D water mass transformation, the tendencies, we only have annual scale right now. And we see that we don't get the right answer or consistent picture with annual fields, which was worth a try, but it's definitely, we need probably monthly data to really do meaningful analysis. Another point is that we also want to include a shortwave penetration, both for surface fluxes, but the boundary forcing will include this term, which is important. So this is one example for the global picture. Then I'm showing another for the North Atlantic water mass transformation here now, presenting results from Mas et al. Again, it's observational based. They used the ocean reanalysis product, OCA, and a satellite observation. So these are surface, also just surface fluxes, surface water mass transformation in temperature space now. And this is now the picture we get from the GFDL simulation just for 5 years. And just a note that here, even though I mentioned before, the convention is a positive G means towards higher lambda here, because we wanted to compare it to Mas et al. It's actually positive means we move towards colder temperature class. So it's more consistent with the density picture, I guess. So that's just so that's why the x-axis is reversed. But an interesting difference is that we overall see agreement. So the gray line here is this so-called 18th degree formation that they showed in Mas et al., which interestingly in the pre-industrial one, it becomes shifted towards colder temperature, so that we actually see rather 16-degree water formation region. So this is, the formation is basically the difference of the transformation, right? You have in this region, and so this is shifted. And then just to drive home the point, the differences, this is now just comparing what we get from the model output, looking at surface as for monthly and annual. And there you see this difference between annual and monthly. That's really the greatest differences. The red is surface and annual, and the blue is the full 3D. So this difference is due to the omission of shortwave penetration in the red one. And then compared to these differences, including the interior mixing term is rather secondary. So it's really clear that the timescale matters. And how to visualize that is kind of if you map this. So like I mentioned, we're interested in also mapping transformation. And on the top, I'm showing you the annual output, and on the bottom, the monthly output. And you can see that really it matters because you need to resolve seasonality. So this movement of the isotherm, so here the 17-degree isotherm, so we are mapping transformation across the 17-degree isotherm, and this movement of the isotherm over a year really influences your results. So this is probably obvious if you think about it, but it's just something that we had to find out. And last but not least, the Southern Ocean. There's some recent study by Moorman et al. That we reproduced. So they used another model, the Access OM201, here in black, and then I'm showing the GFDL CM4 output, and you have they used dense shelf water formation at 32.51. This is now sigma 1. And then map these transformation along the shelf, so at this value. And there's some overall, there are some agreement, but you see also clear differences when you look, for example, the transformation at the shelf is with the higher resolution exosome to much higher than compared to GFDL, even though we see a similar picture with the bottom edge. So in green, this is then the bottom edge that shows kind of this propagation of the Antarctic bottom water. And yeah, that's just one example how we can use that tool to then analyze the different models. So here in terms different configuration, which is mostly probably due to the difference in spatial resolution. And I'm just going to quickly mention that we're also interested in looking at temporal variability. So here's a video of the bottom edge over the 100-year cycle in the GFDL run. And then you can actually match this with this transformation now. It is Hofmöller type diagram in density space across 100-year, where you see this clear multi-decadal variability that could explain this variability in bottom edge. This is just to point out that we interested in moving further, just looking at then other models. And so one tool that we want to use is also part of Pangeo, this looking at cloud archive of CMIP models that we can directly load, and just focus right now on surface water mass transformation. And for now, we just queried the data, what's out there. There are enough, these fields that we need for surface water mass transformation are incomplete, but at least 18 out of 52 have the required fields. So in conclusion, we're pretty happy right now with the current development of the tool, and I think this could be a useful tool that consistently applies water mass transformation in analyzing and evaluating models, especially when we keep the spatial temporal variability of water mass transformation, as I showed. And yeah, it's used both for intermodal comparison as well as assessing differences in configurations. But there's still a lot of work that I'm listing here. For example, further looking into the contributions of specific processes, incorporating inert traces, and then expanding this analysis to more models, not just the GFDL CM4. So with that, I'm happy to take questions.
Thanks, sir. John, Eric. Justin. You're muted, Justin.
That was a very nice talk, Jan Eric. I had a question at your comment. Another tool with water mass transformation is two-dimensional water mass transformation, where you might do it as a function of, say, temperature and salinity. And I think you'll learn a few extra things there, because you might have compensation and density applying to different sets of temperature and salinity, and you can distinguish those. It's been done by a couple of authors. Spear and Zipperman did it early on, I think.
Right, yeah, that's a good point. That's something that we haven't really looked into much, but I know there's probably would be useful also to add to work on.
Okay, there was a question from Paul Dirac in the chat. Is monthly high enough temporal resolution? I think that the next talk will touch on that, but I'll let Jan Eric provide his.
Yeah, no, it's a good point. We are wondering. Actually, we want to test this with model output. So we are definitely certain that we need at least monthly. We need to resolve the seasonality, but we could very well see differences between, let's say, monthly and like a 5-day or higher resolution. And what differences there are, that's an interesting question that we already discussed, that would be where the tool would easily could be applied. You just have two different resolutions and you compare them and see what kind of other features might evolve from higher temporal resolution. So right now we think since monthly is definitely gives you a consistent picture, but from previous studies. But yeah, it's definitely interesting to look further at higher resolutions.
Okay, another question in the chat from Robert Wills. Perhaps I missed this, but has the package already been released on GitHub for others to use?
No, but this is so basically this we haven't released it yet. No, so but this is going to be something on our priority list. So before we wanted to make sure it works, it makes sense, and it doesn't break anything, and we keep you posted on it. I'm sure be within a month or so we'll have a first version up on GitHub. So that's the plan, to have it up on GitHub for everyone then to collaborate also.
What repo should people be watching for that to appear?
Right, we haven't even thought about the name.
Okay.
So, but yeah, X transform was probably that we would think about. Yeah.
Okay. Dhruv, would be interesting to see the impact of temporal resolution of model output relative to the model resolution, reflective timescales and variability present. So agreed, and I think Justin will touch on that a bit in the next talk. Any final questions for Jan Erik?
Yeah, I have one. I can't find my raise hand button, but these comparisons I think are going to turn out to be extremely powerful, as you've shown. But when you compared to model to what you could observe, there was no idea of sort of the scatter in the observations or how close you might be. So I was wondering if there's any thought to some targets, some sort of standard deviation of the observations, maybe from different data sets or something of surface fluxes. But the comparisons you showed, they're significant. Well, there are big differences. Are they significant? Is something along that line about how close one should target models to get to? Any ideas along that line?
Yeah, that's a good point. I think right now we've I didn't thought about like a specific metric or but yeah, we looked, for example, at the mass paper that had two different observational based estimates where we see within these two products quite a different picture. And so, yeah, to derive like a more consistent uncertainty range based on models, based on the observations that, and then fit and see how the models compare to that is a great idea.
Okay. Well, I think we've got a great setup for Justin. Jan Erik, if you could stop sharing.
Sure, yes. Thank you.
Thank you.
All right, thank you, Jan Erik, for meaning I don't have to do any background for my talk, so that's very handy. Let me see. Hopefully you can see something.
Yep.
So I'm going to talk about surface water mass transformation and in particular the role of eddies. And this is work that's been done recently under NASA Physical Oceanography, and NASA Salinity is a new project now. So it's been done with Frank and Lucas Lorindo and Stu Bishop. Dan Witt is now at NASA Ames, Ivana Cherevecki and Mab Maslov. And so that this is a summary, I think, of what Jan Erik was talking about. I'm mainly going to talk about the surface water mass transformation in this talk. And basically, this is just integrating the ASC buoyancy flux between certain isopycnals. And one of the papers that we wanted to address with new data is one by Cherovecki and Marshall in 2008, which is looking at the role of ocean eddies on water mass transformation. And that was a very nice paper where they identified two main roles of the eddies. One is the surface effect, where ocean eddies affect the isopycnal, surface isopycnals, obviously, through the temperature and salinity. And they also affect the air sea buoyancy flux. And for example, the air sea heat flux is affected by the SST in eddies. So that's the surface part. And then there's also an interior part where the eddies affect the diabatic mixing in the interior. Interestingly, they found these effects tended to cancel, which is a complication. But we'll start by just by looking at these surface effect. And I think the advantage of what we're doing, we'll be doing it in a global eddy resolving model, whereas their study was in an idealized small domain model. So I'll be looking at high resolution CSM for this project, particularly focusing on the Southern Ocean and this subantarctic mode water region. I've talked about that before. This is not the same region just talked about by Jan Erik, which is right around the Antarctic Peninsula and coastline. This is equatorward of the ACC. So that the high resolution model, I'm going to use the old ASD run for this one from 2014 with 0.1 degree ocean and 1/4 degree atmosphere. And a good reason to use this, it has quite realistic winter mixed layer depth and SST variability in the Southern Ocean. And I think that's important for this. And in our method, we use daily data of the surface quantities, and then compute the water mass transformation in 0.1 density units. And we'll do a time average over 20 years. So 20 years of daily data. And then to answer actually the question that was raised for Jan Erik, I'm not going to show results from where I looked at different timescales, but I did compare daily data versus monthly averages. And actually they're very similar. It was hard to find a statistically significant difference between the two when I averaged over 20 years. Whereas in this talk, I'm going to talk about doing a spatial filter as opposed to a temporal filter. And there will be some statistically significant differences. That's the first part of the talk. So I'll be applying a spatial smoother. So here's the full case, the high resolution CSM. And this has been introduced again by Jan Erik. This is a water mass transformation plot as a function of potential density and transformation in Sverdrups. What you see is a positive transformation, this transformation towards denser water in this density range here. A lot of this due to heat loss, particularly north of the ACC. And then at higher densities, there's negative transformation that's going towards lighter densities. A lot of that is due to freshwater fluxes. And then the water mass formation is the convergence of this curve in density space. So it's just the negative of the gradient. And you see the positive formation in this band here, which is about the same range as you see in observations for subantarctic mode water. This is the region I'm analyzing. It's a lot of the Southern Ocean. I'm not doing right up close to the Antarctic margin, like I mentioned earlier. So I'm now going to look at the effect of eddies by applying a smoother to the daily high resolution data. And as an example, here's a daily output of potential density from the model. And then this is smoothed. I used just a boxcar smoother, about 3 to 5 degrees. And what you see is you remove the eddying structure, a fine scale structure, but you leave the large scale features intact. Same for the air-sea buoyancy flux, which has large scale and small scale structure to it. My cursor is kind of pointing at the small scale, but there's also a large scale synoptic atmosphere variability. When you smooth it, you remove a lot of the small scale eddy variability, but you leave the atmosphere synoptic. So I'm looking in particular at the effect of ocean eddies, and I'm leaving those atmosphere events in there. Excuse me, I just need to drink some water. Okay, so if you compare the full and smoothed case, full case on the left is what I showed earlier. Smooth case is on the right now, this from 20 years of data. And the first thing is that qualitatively, they're actually fairly similar. You have the positive transformation or densification in similar density ranges on the right panel to the left. You have the minimum in a similar density. And then when you look at the formation, which are the bottom panels, you have formation in a similar density range in both cases. So qualitatively, pretty much the same, but there are quantitative differences. And that's the thing I'll focus on for this first part. So if you use the 20 years of data as the sample size and apply statistical significance with a t-test, you find that you can look at the differences and see what's significant. So this is, the left panel is the difference, the mean difference over 20 years. And if these small boxes are where it's significant. So you can see there's significance in this trough here. This means that actually the full case has a weaker transformation than the smoothed. And then for the formation, there's also a few significant points, and probably the most important is there's this negative difference here is significant. And if you're wondering how to interpret it, this on the right panel is showing individual years, the difference between smooth and full for individual years. And you can probably argue against me on this, but I think this is a robust signal in that this difference always has this trough and then an increase and so on, even though there's year-to-year variability, which is very obvious. And I can even convince myself that this kind of minimum in the formation is somewhat significant. And then we did this kind of analytical decomposition of the differences between the full and smoothed water mass transformation. And Frank was very instrumental in working out this decomposition. I'm just going to show the results here. You can decompose the difference between the full and the smoothed water mass transformation into a part which is due to the small scale buoyancy flux forcing on the left, and then the part which is due to small scale surface density outcrop variability. So that's the wiggles on the surface density outcrops. And then the right panel is a kind of covariability term between wiggles in the surface density outcrops and the overlying air-sea buoyancy flux. And with Stu Bishop and Frank, we've been working on the more direct covariability of, say, SST and air-sea heat flux in our previous work. Now we're looking at a more indirect effect whereby changes to the temperature or salinity in eddies affect the outcrop variability and thereby affect the air-sea buoyancy flux. Anyway, it turns out that this left panel, this is a fairly small effect. This is the effect of having structure, small scale structure in the air-sea buoyancy flux. The middle panel is more important. The values are larger. This is the effect of having wiggles in the surface density and in the outcrop. That has an importance both to the transformation, which is shown in the top panels, and the formation is actually the dominant driver of a difference in formation. And then the covariability turns out to be quite an important effect for the transformation. giving this kind of negative, this trough here. And it's very difficult to see, but this is the full field. And these do add up to the full field of, not the full field. This is the total difference between the two runs. And these three terms add up to this. And you can see that the covariability contributes a lot to the transformation difference. But if you look very closely, this effect of the small scale density wiggles contributes a lot to this minimum in formation. Okay, so that's where we got to on just using a control run and just smoothing the output to look at the effect of eddies. Another way to look at this is to look at the effect of model resolution. It gets a bit more complicated. So do these eddy effects on water mass transformation I just discussed explain differences, in particular for the subantarctic mode water, between low and high resolution models? So that's the next question, part 2. I'll use the same high resolution run from the old ASD suite and compare it to a low resolution run. And the one thing I want to note about this low resolution run, actually the atmosphere is the same, a 1/4 degree. So the atmosphere is actually high resolution. But the ocean has been coarsened to the 1 degree with eddy parameterization. Okay, and these are about 100-year runs. So if we look firstly, how well do they do for representing the subantarctic mode water thickness? This is part of this kind of verifying the model runs I talked about earlier. This is the thickness of the mode water, which is calculated by a classification of densities in this density range, 26.5, 27.1 sigma theta, and a weak potential vorticity, in other words, weak stratification, less than this number here. So this is from Argo, fairly representative of recent observations, and the thickness is up to 700 meters. In the high resolution CSM, you see you have reasonably thick mode waters, but not as thick as in Argo and not quite as extensive. What you do see is that the thickest mode water is in this band just north of the ACC. This is where the winter mixed lead is deepest, and that's seen in Argo and the high resolution model. And then it gets less thick as you go towards the equator. There's advection of, there's subduction and then advection of the water. It kind of travels towards the equator, but it's not as thick. The low resolution run has less mode water. And there's two things to notice here, that it's less thick in the regions where it's a maximum in observations, but also there's not much of this propagation towards the equator. So that seems to be lacking. And I just wanted to confirm this, and I looked at a few years of the run towards right at the beginning of the run, and it did indeed look like these observations. So it has, what has happened in this run, which is it's initialized from observations, is basically stratified this whole region over 80 to 90 years. And a lack of mode water in low resolution runs has been noticed before. This is not a new result. This is a new result. In fact, I did it yesterday. So the high resolution run I've shown earlier is on the left. This is the transformation from the high resolution and the formation on the bottom. Now on the right is the low resolution case. And it's quite different from the high resolution. First of all, this band of positive transformation, which I'm pointing to now if you see my cursor, occurs over a narrower range of densities. So you have a narrower peak. Then you have a sharper trough. And the other thing, interestingly, you have a peak in formation, which is quite strong at about 1026.7. But then this formation is very confined, and then as you get slightly denser, it goes negative, which is not what you see in the high resolution run, where you're still getting some formation, and it's not what we would infer from observations, because observations have a mode water, thick mode water of about 1027. So these differences are large. I've shown them at the bottom here, and they're much larger than we saw from the effect of smoothing the eddies in the surface water mass transformation alone. So really, these are qualitatively different, and they need more work to understand them, and that will come in the future work page. But I'll move to the summary. The explicit influence of eddies on water mass transformation is somewhat small, but it's statistically significant. I'd say it's non-negligible. It can be about 20% for particular density intervals. And in fact, once you remove the eddies from the full field, you lead to a larger transformation in the mode water region. And it's mainly due to the eddying surface density field, in other words, the wiggles. But there is some covariability effect between the wiggles in density and those in the SE buoyancy flux. Secondly, from the part 2, the differences between the low resolution, high resolution CSM are much greater than the explicit eddy effects discussed above. Now we know already that the mean flow is very different between these two resolutions. And I thought there may be a connection with the CPT discussion early on, in fact, that might be an implicit eddy effect on the mean flow, and it would certainly be nice to improve the mean KE in these low resolution runs, because I think that's important to this process. In addition to the mean flow being different, the mean surface buoyancy flux and surface density are different. So you have this whole difference in the mean state, and not just eddies. And further, the winter mixed layer depth is very different. And I was reminded of a paper by Frank and Peter Gent and Bob Thomas from a previous generation of high resolution models that also said differences between the high resolution and low resolution are not just due to the eddies and the parameterizations. In that case, the sea ice difference had a big effect. And that's something we could also look at in the case I'm looking at. A general summary I've found from my work is that higher volume subantarctic mode water is found in the high resolution CSM experiments, which seems to be consistent with deeper winter mixed layer depth. And I would speculate the ensuing subduction and consequent advection of the water towards the equator. And just a few points about the way forward. A lot of this will be done under NASA salinity grant. So we're looking more into the role of salinity transport in the mode water formation and variability. And Dan Witt has already been started work on some of this, and Ivana Cherevecki. We'll be using water mass transformation analysis using state-of-the-art observations, including satellite salinity. And this may relate to Bill's question of Jan Erik about looking at different data sets. We're hoping and planning to use the brief but detailed satellite salinity record from Aquarius. Again, and to use it to understand differences between models and observations. To go beyond just the surface water mass transformation, we propose to do full volume budgets for subantarctic mode water. This is the 3D part that Jan Erik talked about. And we'll be using SOSI as well as CSM for the budgets, and then see if they're consistent with observations. So I think that's it. So thank you, and welcome any questions.
Thanks, Justin. Steve, go ahead.
Thanks, Justin. Great talk, and yeah, great for the organizers organizing the talks. The quick question I've got is with the sea ice effects, and it sounded to me like you're not looking at salt flux and brine rejection and so forth in the contribution to water mass transformation. I guess you're just looking away from the ice edge. Is that why you didn't have any salt in your water mass transformation analysis?
And there's freshwater flux. There's a surface freshwater flux is included, but I am avoiding the ice edge because of more complexity, which I don't want to deal with at the moment. But I'm sure that could be important. So it's probably a way forward.
Okay, thanks.
Steve Yeager.
Yeah, Justin, I was struck when you compared the high res to low res mean formation. It seemed like if you integrated the positive formation, they'd be fairly similar. And so I'm just wondering if it's a question of the low res having a biased mode water density range.
Well, I think this, and it might also relate to the full 3D volume budget in that there may be other terms cancelling the surface water formation. So you're right, you're exactly right. When I showed this, there's this very large formation rate in the low resolution run. And there's actually a hint of that. I have some handy extra slides, and this what I call MR is actually the low resolution. There is a density bin here. I'm showing here the volume in a certain density range where it has this peak formation. And in fact, if you look at the thickness here, this is in a 0.1 degree bin in the low res, and I compare it to the right, which is in the high res. Well, actually, it looks like there's more in that particular bin, but it's in these other bins where it's deficient. So I think, firstly, I think we need to do the full volume budget to understand more. And Ivana Cherovecki has certainly shown that other terms in the budget, like the diabatic mixing, are important. And yeah, I think that's the main answer.
Okay. Any other questions for Justin?
Yeah, Justin, I do have a question, just a clarification. In your discussion, you seem to indicate that when you were talking about the volume of mode water and how little there was in the low resolution, that it was more to do with there was a stratification issue. You said it was overly stratified, but I didn't see that in your summary where you said it was more circulation. Do you have a preference to, was it both, or it was just in the summary slide? I got a different impression than stratification, which is also one of the criteria you have.
Yeah, well, I think, well, in our paper with both authors, we showed the circulation was affecting the stratification. So they're all kind of linked in. So the paper which I led was trying to make the point that the ocean circulation was driving the nature of the stratification. So I probably will switch between the two. And they're both important.
Okay. Any last questions? Okay, I think we can wrap it up for today. Before you go, let me point out that the Land Ice Working Group set the agenda for the morning, and they like to start quite a bit earlier than we do. So we start up at 8:30 Mountain Time tomorrow. And also point out that we slipped Gustavo's talk on the CESM MOM6 current status into that session because they wanted to hear about that as well. So to sort of finish up our survey of MOM6 efforts going on around the community, try to catch Gustavo's talk, which will be at 11 o'clock in the Land Ice Working Group session. And as far as I understand, that meeting will be happening on this same Zoom link that we're using right now. So that we'll be using the same one all week. So anyway, if there's nothing else, I'll see everybody tomorrow morning. Have a good night.
Good.